Stefan. Thank you for coming, dude. I'm excited to talk to you.
Great.
I see my X feed is littered with these types of posts. That there's a sunspot, there's a solar flare, there's a double solar flare, there's all these things happening, these coronal mass ejections that are gonna cause a cataclysm or something like this, and nothing ever happens.
Yeah, there's this interesting, because I cover this in my videos and I talk about it, and it's just an interest of mine, because originally I was focused on the geology and then the geophysics of the Earth, and naturally I had to start studying the space environment to understand what was happening here to a better degree. And so as a result, I learned about this, and I make a video saying, hey guys, we have a solar storm coming in. This is the forecast. Let's say we do see it launch. Right? It's like guarantee we're going to get hit. We have a G3 storm. A lot of people will be like, oh, here he is calling for the end of the world again. It's like, well, guys, I never said that. It's just like this, we have a solar storm coming in. But there's something about the mix of it being epic in scale, because it is a massive explosion on the sun, which is many times the size of the Earth. So it's just fundamentally epic in scale, paired with also a lack of education as to these things. And even adding a third of some people taking these events and then twisting them into a doomsday narrative, and having done that for a long time, that creates this convergence of people thinking that the moment there's a solar flare, we're all doomed. But that is like, we could have what we call a super flare, and we don't know how that would affect the Earth. But in terms of, is that going to happen tomorrow? Or we would need a gigantic sunspot, like unbelievably large, and we would have clear optics on that. And we're not seeing that right now, but it could happen.
What is the biggest solar event that has impacted the Earth the most, like in recorded history, that you're aware of?
Yeah, there was a really big, this is kind of a complex question, but in 1859, there was a Carrington event. That was a really big solar flare, and coronal mass ejection, impact, and a really strong geomagnetic storm. We've had other Carrington level solar storm impacts since then. 1872, 1921. We kind of got lucky in 1972. It didn't have the right magnetic field configuration, but it was strong enough to set off these landmines at Vietnam.
Whoa.
Yes, that's an interesting one, because they just deployed these landmines off the coast of Vietnam. Then we had this super fast solar storm impact, but again, the magnetic field wasn't conducive for a really strong, like, magnetic storm where the magnetic field's going nuts. But it's still enough of a shock impact just because of the velocity and the density that these sea mines like went off. That was 1971. We had a close miss in 2012. Some people know about that. But those are, let's say, a Carrington level event. There's solar storm impacts that are less than that, like what happened in May 2024. That was a big solar storm impact, actually multiple in a row, that triggered what's known as the Mother's Day storm, or the Gannon storm. This is May 10th to the 12th of 2024. During this solar maximum, that was big, but that's quite a bit weaker than like a Carrington level impact. But if you go back, we have these isotope records where we see these radioisotopes jump up dramatically, like carbon and beryllium. And we don't exactly know what caused those to go up. It could be a solar storm impact. That's the most likely candidate, but it could be cosmic in origin. They're called Miyake events. And so if it is solar in origin, then that's classified as a super flare. And that is about 10 times bigger in scale and stronger in scale in general, if not even like up to 2 orders of magnitude stronger, 100 times stronger. So those would be the largest. But in terms of us having like really hard data on that, we don't. So 774, 775 AD, we had a really powerful Miyake event. You can go back through the record. We had some really powerful ones. They kind of come in clusters, it seems. But going further back, there's also a really powerful Miyake event that we're starting to get good data on right around the border of the Younger Dryas event. So that's kind of interesting because it like lines up pretty closely with when that cataclysm went down. And there's some people that talk about there being a solar trigger for the Younger Dryas, and then other people talk about, comet trigger, or maybe it's just orbital cycles and Milankovitch cycles and such.
Right.
But I think it was a convergence of factors. But yeah, the point is that we can see a small a small solar storm come in and let's say trigger a G3 geomagnetic storm, that's a moderate to strong one. We can see a Carrington impact, how that would affect technology and like satellites and power grids and more. Nowadays, we don't really know. Then we could have a super flare, and that certainly wouldn't be good.
What would happen during a super flare?
Well, we don't really know because these power systems and tech and everything has been hardened quite a bit, but I do have a feeling that if we had a super flare, like we had a really big super flare, we'd probably lose a lot of satellites.
So it'd be like a giant EMP.
That's exactly what it is. It comes in so fast that not only is there a massive electromagnetic pulse, which can cause a lot of satellites to undergo what's known as deep dielectric charging. They can short circuit. You also get the upper atmosphere of the Earth to actually energize and raise up. And so the density of the atmosphere increases in some aspects. And so these satellites in low Earth orbit all of a sudden encounter more drag. And as a result of that, they will often lose their altitude and burn up.
Whoa.
And so we have quite a bit of data there in terms of Starlink, in terms of there being just regular solar storm impacts. And then we see some Starlinks are falling out at rates greater than maybe Elon would hope for. But they're always launching more and more up. So they're kind of replenishing. But if you had a super flare, like a real legit super flare directly aimed at Earth, impacted, I think probably the majority of satellites would go down. We don't know, but that's probably what would happen because it'd be so far beyond what we've experienced. We already see we already see the effects of what's been happening. And it can be pretty severe with some of these smaller solar storms. And then power grids, I think there'll certainly be blackouts globally, but maybe not one massive global blackout, but isolated, maybe larger. It's hard to say, but it would be a huge black swan event.
What happened? Can you lay out what happened during the Carrington event? Like how bad were we affected by that?
We weren't that affected technologically because we only had telegraph lines.
This was in the
then.
1700s, 1800s,
1859.
1859. Yeah.
And that was the first solar flare that was observed on record. Carrington, this British chap, was looking at the sun and he saw it start to flare. And then he ran to go grab like an aid or something to tell them. And he actually missed seeing the peak of the event, like that 1 minute where it's really going nuts. Then he came back. This is what they've kind of been able to reconstruct historically. Yeah. But that he saw effectively the flare. They estimate it was up to like a X65 flare. There's different categorizations. It's logarithmic. So you go from, let's say, C to M to X. Those are the three highest. That's a 10X jump each time. And if you have an X65, then that's 65 times more than X1. So a huge jump. That's some of the estimates are in that zone. It could have been less. We don't know. We don't have the modern tools of characterizing these events back then as we do now.
Sure.
But in less than 24 hours, I think it was about 16 hours or so, maybe less than that. It wasn't more than 12. We had this impact come in, and all of a sudden telegraph stations were catching fire and lines were like melting. And there were some reports where they disconnected the power and they were still able to operate their machines. Because as that solar storm hits, you have a whole bunch of high energy particles. This is really if we really zoom out and look at the Earth as a whole, we have to be very thankful that we have a magnetic field because that protects us from high energy particles from space, cosmic or solar. And if we didn't have that, things would not be good. If you want to colonize the solar system, you got to figure that out because most planets don't have a magnetic field, or moons, for example.
Right.
Jupiter, Saturn, Uranus, Neptune, they have magnetic fields, but they also generate their own super high energy particles. So the radiation.
Mars has a magnetic field, doesn't it?
Just crustal anomalies. No globally generated magnetic field.
Oh, whoa.
Yeah. There's ideas that you could put a big magnet in front of Mars and keep it in line with the sun and basically create an artificial magnetosphere, but I'm not so.
Is that one of the biggest issues with colonizing Mars?
It'd be a big one. Yeah, it'd be a big one because Mars is still close to the sun. There's also like the fact that I don't think a lot of us realize just how close the Earth is to the sun.
Right.
At 1 astronomical unit, we think Mars or Venus and Mercury are closer, and they are. But Jupiter's at 5. That's actually still very close. Saturn's at 10, Uranus is at 20, Neptune's at 30 astronomical units. It drops off quite a bit when you go that far out. But when you're at 1 AU, you're getting like really walloped. So we have a strong magnetic field on Earth. It's actually very strong if you look at kind of the solar system scale. Mercury's field is 1/100th the strength. It's very, very minor. Venus doesn't have a magnetic field. Mars doesn't have one.
Why do we have such a strong magnetic field?
Because we have a lot of internal processes within the planet. Our planet is very active and alive, whereas Mars seems to be dead geologically for the most part. They did register like a magnitude 4.6 earthquake on Mars in 2022, I believe. So that's pretty big. But, we get like magnitude 9.5s and probably larger. But we have a lot of active processes, and there's a lot of the research in geophysics across time has been trying to figure out how Earth has been able to maintain its energy and heat for billions of years. And so it's kind of like Earth in many ways is a macrocosm of life. We don't really know how it keeps going and replicating, but it does. And that generates a magnetic field, these geodynamo processes. And I think there's probably some other factors involved as well.
Interesting. So for people who aren't familiar, can you basically lay out what geophysics is, what the idea of this is, and how you got into all this stuff?
Yeah, geophysics is just examining the physics of the Earth. And you could broadly apply this to the other planets as well. Maybe the quantifier geo goes away at that point. I'm not sure. But there's a lot of energetic processes unfolding on the planet. A classic example is that there's an earthquake, and there's some just event that occurs underground. A fault slips. You have a movement in the crust, and that releases a tremendous amount of energy as seismic waves. This is sound energy that radiates out. There's broadly 3 different types. You have P waves, S waves, and surface waves. So it's a compressional wave, a shear wave, and then these rolling surface waves where most energy is. And some people actually feel that. So that's like a well-known geophysical energy. But then you also have the magnetic field, and you have these telluric currents, these electric currents that pulse through the Earth. Those are really interesting because we really don't know too much about them. There's lunar rhythms to that. There's solar rhythms to that. Those are greatly enhanced during a solar storm impact and a geomagnetic storm. You have these telluric currents don't just go through the crust of the Earth. They also go through the oceans. The oceans are very conductive. I think most people in this field aren't thinking about the oceans enough in that regard. And these electric currents are also pulsing through the upper atmosphere, the ionosphere, which is how they get induced into the Earth's surface in many ways. So all these combine create this geophysical system that's multi-layered and also interconnected. And what happens in the space environment affects what happens in the atmosphere and in the surface and even down into the core. Just to what degree, what's the significance, how so? These are all in some aspect open questions, not completely open, but because we're not clueless, but we're also probably more clueless than we are educated and, and super deep understanding as to what's happening. I think in general, my kind of thought in general for this is that we really are pretty new to understanding just exactly how the energetic system on Earth works. And I think it's much more alive and you could say even conscious than most people attribute that to the Earth at all. Because a lot of people just see the Earth as kind of like a dead thing. But again, like how is it still sustaining itself after billions of years? Whereas Venus has just become a hothouse and Mars is dead. And there's a lot of unique properties to the Earth. And it seems, well, across time, people thought of it as intelligent. But
for some reason, most dress shirts always make you choose between looking good or feeling comfortable. Mizzen and Main is the first brand I've ever worn that gives me both without having to steam clean or dry clean. It's the most comfortable dress shirt I've ever owned, and I don't even like to wear dress shirts. But when I wear this thing, I don't mind because it's so stretchy, soft. It actually keeps me cool in the hot Florida heat, like when I'm going out golfing or whatever. Yeah, it's beautiful. Mizzen and Main makes classic menswear using performance fabrics, so looking put together doesn't have to feel like a chore. They actually invented the performance fabric dress shirt over 10 years ago, and they've been refining it ever since. Their shirts and pants look polished, they feel stretchy, lightweight, moisture wicking, they're wrinkle resistant, and they're completely machine washable. No iron, no dry cleaner, just throw it on and go. Whether you're in the office, traveling, golfing up a sweat, you feel the difference immediately. Professional style that flexes with you. Mizzen and Main is a veteran-led company that gives back, offering a year-round military discount and supporting veteran foundations. Right now, Mizzen and Main is offering our listeners 20% off your first purchase at mizzenandmain.com by using the promo code Danny20. That's Mizzen spelled M-I-Z-Z-E-N and Main, M-A-I-N.com. And use the promo code Danny20 for 20% off. Mizzenandmain.com, promo code Danny20. But if you'd rather shop in person, you can find Mizzen and Main stores in select states. Yeah, it's interesting too how the telluric currents in certain parts of the world will directly correlate with like lightning strikes. You know, with like the upper ionosphere and like thunderstorms and this kind of things, and like rain and lightning and the charge in the earth being directly correlated with all this stuff. It's just wild how it does seem like it is alive.
That's my impression. And if you go to a lot of these ancient sites have been built in those areas, and if you go to them, you kind of feel it. Mm-hmm. I mean, we're resonant with the earth. Our brain waves are the same frequency and strength as Schumann resonances, which are one of the byproducts of all these geophysical energies. Mm-hmm. These are frequencies of about 8 hertz, 14 hertz, 20 hertz, 26, 33, 39, 45. They fade as you go up higher in frequency. But that's the same brainwave architecture that our brain uses. And if you go to those sites, there seems to just be kind of a change that you experience, especially if you're more sensitive. Telluric currents are interesting because the positive energy accumulates in topographically elevated areas. So like hills and mountains will accumulate a positive charge. And if you have a change in the charge of the surface, you're affecting the flow of energy going through the atmosphere, the atmospheric electrical current, because the ionosphere is in general pretty stable in terms of its electric potential. A lot of this is we also think mostly, like the mainstream, I guess you could say, or just people's understanding is that they look at this often just from a magnetic perspective, but I think the electric perspective is really also just as important. I mean, they're two sides of the same thing. So looking at the electric field dynamics is really important. Mm-hmm. And so I think just across time, people felt these areas intuitively and happened to start building things there, or I think there was also a deeper connection and understanding to this in the past, but we're starting to reclaim that, I guess you could say.
So what made you get interested in geology in the first place?
I guess I just liked being outside, and I just always had fun. I was originally going to be a history major for college, and then I took a geology class, and I just did really well at it. I was like, this is great. And the more I've gotten into it, the deeper I've like a connection I felt to it. And I guess I just have a really macro brain. I just like to see the really big picture. And I think one of the best things that I've done is through the study of geology, I've developed a sense of geologic time, and that broad time horizon, building those neural connections to kind of grasp at that as best as possible has helped me in a bunch of other ways with smaller time dimensions. And then from that, it's fairly easy to branch off into the space environment and cosmological environments and not get totally lost, because if your mind is set on just the daily frequency, it's going to be hard to grasp some process that unfolds over 1 billion years, let's say. Yeah. And I don't think it's easy for anyone to do, but if you train that, it gets a little easier at least. And so I just think it's fascinating what the Earth is and what we don't know about it still, and maybe what the ancient people knew a little bit more in certain aspects, and what's there still to be discovered. I mean,
it's also fascinating the amount of minerals and natural gases you can extract from the Earth. How do we come up with that? How did geologists come up with the hypothesis that like this is where we can go drill for oil?
Yeah, that's mostly based off of seismic reflection, marine seismic reflection mapping. So they'll take a boat out and they have a whole bunch of seismographs, basically like these seismic tow, these tow cables where they have a whole bunch of seismographs in them, and then they have this massive like sound pulse, like sonar pulse.
They'll drag it like under the water?
No, it's at the surface.
Okay.
Though they can be submerged at depth a little bit too, but generally they're floating at the surface, and then they're using these massive sonar pulses. And as a result, you'll get these reflections off of the different layers. Yeah.
Oh, whoa. So it goes into the rock, into the surface, like underneath the ocean floor.
Yeah, hydrophones is the better term to use. But yeah, you'll get first a reflection off of the boundary between water and sediment, and then you'll get different reflections and off different layers. And those are pretty easy to categorize. So there's a lot of processing that goes into it. But if you get good data, the cross sections are really quite illustrative. And you can see what's hard rock, what's sediment, for example. There you see that like kind of sediment cap in the valley. But you can use that to.
So this is all like sound type stuff, like sound technology.
Yeah, that's all seismic. So you're not really using much in terms of like, for example, magnetic field exploration for oil and gas. It's almost all seismic. Sometimes you'll do some mapping with like tellurics, like magnetotellurics, but that's typically on land. But there's all these different tools that we have. We can look at gravity and gravitational anomalies and like the variations to understand the subsurface. We can look at, of course, seismic. We can look at tellurics. We can look at the magnetic field. Those are the main ones. There's offshoots of those. But the key with geophysics is to put at least two of those together and see if they agree at least on some sort of anomalous result, you could say. Because if they both point to the same area saying, hey, this is a little different, then you have a pretty good sense that there's probably something there. If you use just one technique, then it may show something, but it could just be a fluke, noise, anomalous, whatever. So that's if you're ever tracking this stuff and someone's come out with like a discovery or something and they're using geophysics, if there's not two methods being used at least, then you should just look at it, closely and not just immediately take it at face value. Because that's a common thing. Like, oh, we just did this one method and like how you do the survey matters. Like I think they did this seismic survey of the Sphinx a while back. Some people have talked about this and they found this, void under like one of the paws, I guess. I can't be the end all be all definitive answer on this, but looking at the way they laid out the survey, if you don't have seismograms over that void area and you're only getting it from the side of the Sphinx, it's going to be hard to get good resolution where you think you're looking. There's certain rules that you can follow and maybe there's something there, but it wasn't confirmed with other methods as well. So sometimes you have to be careful with those results because it is very indirect. Everything's super indirect with geophysics. So you have to pile these techniques together, and when they all confirm something, then you're good to go.
Right.
Or with the marine seismic, we've been doing it so long, and they have so many results that these marine seismologists are really good now. And they can just look at a cross-section and be like, boom, there's your oil. Drill, baby.
Wow.
And then they go in with the horizontal drilling, and they use the magnetic field often.
Horizontal drilling?
Yeah, for fracking.
Oh, okay. Yeah,
They'll drill down, but they keep track of where that drill bit is in many aspects. Like sometimes they'll use the magnetic field. They need these ultra high resolution magnetic field models and measurements, so then they can track where it is. Because you can pick that up anywhere on the Earth. Doesn't matter where you are, you can measure the magnetic field. And so if we have a super high-res model, which different government agencies release at a regular update frequency, if they need to change it quickly because the magnetic field has changed quickly, then they'll do that update. That will allow them to precisely pinpoint they're exactly there in that stratum, that layer, and you're good to go. We're right on the area that we found earlier with the.
But it's always a
seismic.
gamble, right? It's not always 100%.
Yeah, I don't know what the
like
the.
I'm sure it's always a risk, like when you're drilling. I mean, I don't know shit about the oil industry, but I watched a TV show about it.
Okay.
I imagine that there's a huge risk, like when you're, taking all that equipment and risking all that money to like go like set up a drilling up. Because I've heard stories of like the wells that they have in Venezuela, and they take years to drill them. So I can't imagine. Do you have any like former friends or acquaintances that you went to school with who got hired by big oil companies?
I'm sure I do. One of my buddies in San Diego, he's a Venezuelan, and he actually is in marine seismic, and so he processes all that data and everything.
No way.
There's a lot of geophysics that's being done in South America. People from Brazil, Venezuela, because it's a field that has a lot of opportunity in it. It's also very interesting. It's dynamic, and so a lot of people get into that. And then if you're a geophysicist, you can kind of go anywhere in the world if you want to. If you are more on the research side, there's tons of conferences everywhere. So it's really a pretty cool industry, field, niche that is really always in demand, doesn't experience like setbacks. When there's recessions, for example, there's always typically, there can be big booms and busts with oil and gas, but there's always demand for Earth's resources. That's never going to go away. And so our understanding of the Earth is basically only going to go forward with time, as I see it. Maybe we'd have to have some sort of cataclysm to take us offline, I guess, for that to stop. But there's this need for society to continue, for there to be increased geophysical understanding, geologic understanding of our planet. Or else if we don't have the resources we need, it's, all of a sudden we're stagnant.
How many other geophysicists do you speak with or do you keep in touch with?
A few, not too many, honestly. I'm kind of in my own bubble with my research and stuff, but every now and then I'll touch base with, acquaintances, and I want to get
back. You guys
back.
Like compare notes or anything, or talk about?
Well, I'm a little different in the fact that now I make a lot of educational videos, and I explore a lot of kind of offshoot ideas for geology, geophysics, space weather, and also most geophysicists, let's say, aren't really concerned about space weather unless they're like doing a magnetic field survey, and they're not going to get good data if there's a geostorm because the magnetic field's going nuts. So they may learn a little bit about it then, but unless their interest takes them there, they're probably not going to learn about that. So there's these kind of silos in the sciences where people just stick in their one box, and very few people venture to explore the others. But I feel like if we're going to understand things to a better degree, we kind of need to go interdisciplinary. But the normal workforce doesn't reward you for learning about this thing. If you're a magnetic field surveyor, and what is learning about solar activity, how does that help you or your paycheck? But I've been able to kind of buck that trend by extracting myself from the normal system and just floating on top of the ocean of internet interest in education and such. And so I have free reign to. Did
you have a traditional job in geology before the YouTube stuff?
Yeah, before I launched into YouTube, I was doing a lot of field work out of California, and then also I've had two main like geology jobs before I just launched into my own research and video production. The first one was a lot of field work in and around the Bay Area, but also further abroad.
San Francisco.
Yeah. And then, so that was a lot of seismic surveys and a lot of ground penetrating radar. I was using that a ton. I'm really good with GPR, though I haven't done it recently, but.
For what? Like for what?
So there were some archaeological investigations that we did. One in particular this was pretty cool. There was a Japanese POW who was buried in one of the like marine camps, or I think it's the one in Monterey, California, one of the military bases there,
Okay.
where they train soldiers and everything. I don't remember the exact name of it, but it's in Monterey. And they buried them there, and the Japanese wanted to bring them back. And so there wasn't really much for the remains, but they knew the plot where he was because there was like different headstones. And so they hired my company, and I was the guy sent off to do a GPR survey of that location to try to find those specific remains because they didn't want to dig up the whole thing. It'd be a whole crazy thing. And they probably chose me because I can get very detailed. So I like finely tuned the settings on the device we had to like get the most data possible. And it was kind of tough conditions because it was raining. And when you have clay soil, it's wet. It basically absorbs all the energy. So it's hard to get good data. But I was able to find some anomalous signatures with the GPR, and then they dug there, and turns out we were right on. They got the POW.
You found it.
Yeah, and that was like a really big event too, because it was the first time, from what I remember them telling me, it was like the first time the Japanese had come over to do this sort of like ceremony. It was like a big ceremony between the two to then get those remains and then bring them back to Japan. So that's one example. A lot of work was also done looking for utilities, but sometimes it's like we need to find this big line that's buried 12 feet down and we have no idea where it is. So a lot of like detective work goes into this.
2026 begins this month, and every year I tell myself the same thing. I want more energy, better focus, and faster recovery. And not in the New Year's resolution way. I mean actually feeling sharper and stronger day to day. And if you're around my age, you've probably noticed, even if you're training, eating right, doing all the things, your energy just isn't what it used to be. That constant brain fog, slower recovery, feeling worn down for no obvious reason, there's a real culprit. It's NAD. By the time you hit 30, your NAD levels drop by almost 50%. And NAD is critical for how your body creates energy, repairs itself, and keeps your brain firing on all cylinders. And that's why I use Row Nutrition's liposomal NAD. And I'm not exaggerating when I say the difference is noticeable. The energy is clean and steady, the focus is sharper, and the recovery is way faster without having to rely on caffeine and stimulants. NAD fuels your mitochondria, the powerhouse of the cell. And up until recently, replenishing it meant expensive clinic visits and IVs. But Row uses an advanced liposomal delivery system designed to help your body absorb NAD efficiently without the hassle or insane cost. I've been using Row's liposomal NAD consistently, and it's already become a staple in my routine. You're seeing pro athletes, trainers, and health-focused people all leaning into NAD, and that's for a reason, because it works. If you want to start out 2026 feeling your best, you can try it risk-free with a 60-day money-back guarantee, plus get 20% off by using the code DANNY at rownutrition.com. Again, that's code DANNY for 20% off at rhonutrition.com. So for GPR, how do you do that? What do you like, fly a drone? You fly a plane, fly a kite? How does it work?
You can fly a drone. I don't think they have GPR from planes, definitely not kites now, but they do have drone-based GPR, which is cool.
Okay.
But generally, you want the antenna to be as close to the surface as possible because this is basically it's a low-frequency antenna. You can almost think of it like a radio dish. And that's broadcasting electromagnetic waves into the ground. And it's also looking for reflections on those. So a lot of the physics is the same, whether it's electromagnetic or whether it's sound waves, right? Seismic or GPR, it's the same deal. And different frequencies will give you different depths of penetration, and certain geologic materials or even man-made materials like asphalt, for example, will behave differently. How does water affect this? That's a big thing too. Cool thing with GPR is these electromagnetic waves pass through ice super easily. So that's how they've done a lot of mapping of, for example, like Greenland and other places like that, because it can go through the ice like many kilometers, many miles. And so they can get really good data there with these low frequency antennas. They drag those behind those like massive, it's not a snowmobile, but those big snow vehicles that they'll drive. It's almost like a tank. So GPR works on that principle, and you get these waves to reflect off the layers, and then you can look at that. And there's a lot of,
Oh, wow. Okay.
That's a pretty interesting one.
Whoa.
But yeah,
so that thing in the front is the device.
Looks like it. Yeah. I've never seen that one.
Wild.
But a lot of GPR now is done for road scanning to find, let's say, like potholes and such. So that could be a good example. So there's tons of applications for this, and it's cool to see it grow. Now they're doing the UAV GPR,
right?
Because you can cover really vast areas with that quickly. But the difficulty is that you have to fly it close to the ground. You have to account for the elevation changes.
Right.
So you need a high resolution map of the topography, which usually involves LiDAR. And then you also do get a dissipation of the signal and a reflection off the surface of the ground. So ideally, it's typically right close to the ground, and you're dragging that kind of sled or box. But there's tons of ways to do it. It's a huge field, and they keep finding more and more utility for it.
Would there be a way to do it well out of an airplane? Or would that be too far from the surface? Like we don't have that kind of technology yet. Will we ever be able to do that, do you think?
I think it'd have to be a low enough frequency for that. And there's also the issue of maybe the plane is moving a bit too fast to accurately get the nice reflection. I mean, this is light, so it's pretty quick. But there is an aspect of a lot of this data processing and just collection where you need enough stacking of data points. If you just get like 1 or 2 data points, your signal to noise ratio isn't good enough. So you want to be able to like hyper stack this, for example. And I'm not sure. There's probably people that have experimented at a minimum with GPR from a plane, but I know with UAV tech, that's a big area of exploration. They do a lot of magnetic field surveying with planes. And they do that for mineral exploration. Like that's a very common thing. Yeah, especially up in Alaska and Canada.
The magnetic field is correlated with minerals in the ground?
Yeah, because a lot of minerals are either alter the magnetic field locally, like they have their own magnetization to them, or they are associated with magnetic minerals and just, let's say, geologic layers in their creation, let's say. So you may not be looking, I don't have an example off the top of my head. Just there could be some sort of mineral that's not magnetic, but maybe it comes with a lot of magnetic minerals normally. So you look for that signature. And then a lot of minerals also come from, for example, like past impacts, which is interesting. So that will usually leave a magnetic signature. So if you get this impact coming in, and then that creates remnant magnetization, and also perhaps, let's say there's an asteroid, it has a whole bunch of magnetic minerals in the first place. Often it's those deposits which are super enhanced compared to normal. And when it comes to mineral exploration and mining and stuff, often it's just a percentage equation. If you don't have a enhancement that's high enough, it doesn't become economically feasible.
Sure.
Whereas like some of the gold production in Nevada and other spots around the world, it's like just barely feasible because they're crushing up so much tonnage of rock just to get like a gram of gold. But because the price is there and, it's just feasible. But if all of a sudden you bumped it up 10 times, they'd be like, let's go.
Right.
So they look for those impacts often or geologic features which naturally condense or refine whatever they're looking for.
What's the deal with this South Atlantic anomaly? Are you familiar with that?
Yeah.
There's some sort of like hole in the electric field there, like somewhere in the Atlantic, like Southern Atlantic Ocean.
Yeah. Off the coast of Brazil. An easy way to think about it, this isn't exactly precise, but if you think about Rio de Janeiro, that's effectively the center of the magnetic anomaly. It's the largest magnetic anomaly.
Oh, interesting. So you can find an image of it, Steve, or like a illustration.
Yeah. And so this is where the magnetic field on the Earth is the weakest, and quite a bit so. It has been growing, it has been weakening at a rate that is measurable in the human time frame of years to decades. So it's pretty significant. If you look at the history of magnetic anomalies, there is quite a rich observational record of positive and negative magnetic anomalies that are transitory. So they exist for, let's say, 200 years, 300 years.
Oh, interesting.
So we don't fully know how long this magnetic anomaly is there. And the physics of it's pretty complex. The general idea is that there are these patches of reverse flux that are deeper within the Earth near the core mantle boundary. The core is where the magnetic field is generated for the most part. I also think that there may be some magnetic field generation in the mantle and further up, but that's a whole different conversation. But if you have this patch of reverse flux that is canceling out the positive flux, let's say, like the positive magnetic field, and then this one's coming in with the, let's say, negative magnetic field, they're just going to equalize. Mm-hmm. And so the overall field strength would be greatly reduced as a result. And so that's what we see with the South Atlantic anomaly. And as a result of that magnetic field being so much weaker, the strongest magnetic field strength on the planet is Antarctica with the south magnetic pole.
Right.
Or rather, the magnetic pole in the southern hemisphere. It's actually a positive magnetic pole. But regardless, that's about 67,000 nanotesla, which is
how much again?
67,000 nanotesla.
67,000 at the South Pole.
Yeah, or we could say it's a 0.67 Gauss. There's different, varies of values that you can use. Mm-hmm. But at the South Atlantic anomaly, it goes down to like 22,000 nanotesla or 0.22 Gauss. That's like a third as much. It's really quite weak. So you get a lot of cosmic rays that come in there. That affects satellites.
That eats up like most of South America.
Yeah, that's a reason why they're all dancing and going crazy down there.
You think that's it?
I do, actually, yeah. First time I went to Brazil, I was like, it is definitely different down here.
Well,
yeah.
How long has that anomaly been there?
That we don't know. We have some data. So the first good magnetic...
When were we able to first start measuring it?
Yeah, exactly. So we first started getting relative magnetic field measurements either in the late 1600s or certainly in the early 1700s. And that would be where they take a magnetic field measurement in their location. This is mostly by ship, right? And then they would track it as they navigated across the globe, but it'd be fixed at location. Then we developed absolute magnetic field measurements around the middle 1800s. It's like 1830 or so. And since then, we deployed more and more of these stations to be able to get good magnetic field measurements across time that are absolute in scale. So everywhere can be compared to each other. Whereas with the relative stuff, it's hard to piece it together. Also, across history, we've had really good coverage of the northern hemisphere versus the southern hemisphere, because most of the land mass is in the north, most of the population's in the north, and most of the ocean surveys were in the north. So our maps that we reconstructed from the historic data for the 1700s and even earlier have very limited coverage where the South Atlantic anomaly is. There is evidence that it existed during this time, but you can't really go really beyond that in terms of saying it. Some people think it's been around for like hundreds of thousands to millions of years. I'm not so sure about that, because we've seen positive flux magnetic anomalies that have popped up suddenly and then gone away. The Levantine Basin, Western Europe, Hawaii, Japan, a lot of these places have experienced where the magnetic field suddenly strengthened dramatically. The field strength, as I said, at its strongest right now, Antarctica, 67,000 nanotesla. There's evidence from the Levantine Basin where it was like 120, 130,000 nanotesla. But that was just like a transitory pulse.
Where is that?
It's like Israel and Lebanon and that whole area.
Whoa.
And the magnetic field was stronger back 1000 AD and then also 1000 BC. Those are the two rough dates where the magnetic field overall was stronger.
How do we know?
That can be tracked a few different ways. You can measure the remnant magnetization of, let's say, like a lava flow.
Oh.
Because these are lava flows. Magma has a lot of metallic minerals in it, like magnetite, titanomagnetite. And so they will, upon cooling, lock in the direction and strength of the magnetic field. But we also have limited lava flows. Like we don't have global coverage.
Right.
We don't have a lava flow at every single point on the planet. So you can do a lot with that.
Interesting.
That's probably the most useful. You can also record the remnant magnetization and the intensity, direction, all that stuff from just magnetite or other magnetic minerals that settle out in sedimentary layers. It'll be very, very low density, you could say, because you have a whole bunch of, let's say, like quartz settling out, which isn't magnetic. But if you do a drill through, let's say, a lake floor, and you get that that tube of sediment, then you can kind of chronicle the magnetic field that way. So that's another one.
It's like a proxy, basically, for what was going on with the magnetic field.
That's another good one to add in. And then the one that I think is the coolest is anytime you fire up pottery, you're also generating effectively a magnetic signature at the time that the pottery cooled at. Because what happens, there's something known as the Curie point, whereas if something heats up, these magnetic minerals, if they heat up beyond about 650 Celsius, I believe it is, they lose their magnetization. So if they recorded a prior magnetic field measurement, if you heat them up, they lose it, and then they cool down, they'll lock in whatever the new one is at the time of, let's say for the pottery, time that it was fired and cooled down. So we have archaeointensity data from all these pottery sherds that we find across the world. And so we have really good coverage of the magnetic field measurements, for example, the Levantine, because there was so much, pottery and civilization across the years. And talking to Matt Bell recently, and he's a pottery freak because he has all the Egyptian vases and everything. And he said that something about them now finding pottery that goes back like 10,000, 12,000 plus years, like way further back than like beyond Göbekli Tepe. So I'm not sure if they've done any archaeointensity data recovery from that, but if they start, because you have to take a little bit of it and damage it, but if we do that, we could get even more information, high quality information on Earth's magnetic field going back in time.
Could you carbon date that? I guess you could. I guess there could be carbon in like clay, right?
Maybe it's a little bit. Yeah, I'm not exactly
like traces of it. Maybe, I don't know.
Yeah, I don't know exactly how they date.
Depending on what it was made of.
Yeah, they definitely do radioisotope dating on this, whether it's carbon or otherwise.
Oldest pottery, and I'm not even going to try to say that.
20,000 years old, though.
Yeah, 20,000.
Where was it? Oldest pottery found yet, dated about 20,000 years. Both.
Jianrendong.
There you go. Fucking, you nailed that.
I think so. Yeah.
Nice. Jianrendong, and go ahead, try that one.
Yuchanyan.
Yuchanyan. There you go. The Yuchanyan caves show early use of pottery by hunter-gatherer communities in China.
You wonder if those were fired or whether they were just, they took like wet clay and just molded them and let them air dry.
Right.
Because if you fire it, then you'll get that magnetic signature at the moment.
So go down, Steve. It says that those caves in China are the oldest of the growing number of sites which support the origins of pottery as having occurred not just in the Japanese island of Jaman culture of 11 to 12,000 years ago, but earlier in the Russian Far East and South China. Whoa, 18 to 20,000 years ago.
Yeah, that pushes it back. I was aware of
That is bananas, dude.
I was aware of the Japanese stuff, but this must have been what Matt was referencing. Or even further back. I mean, he's definitely super interested in all this.
Yeah.
But if they start dating that, then that's going to be really, really useful information.
I had a guy on recently, what was Max's specialty?
He was a nuclear physicist.
Nuclear physicist who did analysis on those vases that Matt Bell gets, the granite ones. And he basically, I don't know if he proved it, but he's pretty confident that they're all modern. Like they were made in like modern factories, or they were using some sort of like machining, like modern tooling or whatever. And they weren't like the super precise ones that seem like impossible. They weren't from like super ancient times. And he's also been on Matt's show. So it's super interesting stuff.
Yeah, it's been a cool story to watch because it's one of the few things with this ancient history community and those that have interest there that you could see the ideas and then the scientific method get applied and then kind of now the results and discussion following it. And there's going to be more to that, I'm sure.
Yeah.
But a lot of the ideas that float around just in general, let's say, in the zeitgeist and on the internet and everything, they just kind of remain unproven and no one takes the initiative to explore it more. And so it's been cool seeing multiple independent groups and people look into that.
Yeah.
and come to some sort of conclusion on it.
Yeah, it's been fascinating, especially people like Max, who is able to, shatter his own dreams by disproving it because, he wanted that to be real. So back to that Southern Atlantic anomaly. How does that affect us? Like, is there any sort of implications on that to the rest of the Earth or that area of the world?
So the implications right now are that if satellites fly through that area, they often get hit with more high energy cosmic particles, or during a really intense solar storm impact, more high energy particles from the sun.
We'll get through there.
Yeah, and that can affect the electronics and such. But in general, it doesn't seem to be that big of an issue from that aspect. In terms of the biology, that's really interesting. Something we don't know much about, but the more you learn about bioelectricity and everything, we see how we're connected to all these energies. I mean, we're in resonance with the Earth across the board. So
you're really getting multidisciplinary now.
yeah, so there's a lot of interesting stuff there, but we don't have much like data on that, you could say, in terms of like the direct impact, let's say, on the South Atlantic anomaly and, heart attacks in Brazil.
Sure.
That would be interesting data. We see a connection between heart attacks and geomagnetic storms and other things like cardiovascular issues, but there's some like really precise, detailed stuff that we just don't have data on.
A lot of crazy UFO stories from Brazil. We just had a crazy podcast about that last week.
I had a dream where this is like maybe 18 months ago, 24 months ago, where the UFOs, the aliens announced themselves in Brazil.
Oh, God.
And I woke up, I was like, that makes sense.
Oh, dear.
There you go, peeps.
There you go, folks.
Yeah, it was odd, but I was like, that makes sense. I could see them being like, hey, well, this is no different than what we already have because it's already so culturally diverse there.
Oh, my God. Yeah.
But in regards to so that's with the Atlantic anomaly, like the real world implications now, not really too crazy. But if it continues to weaken, if it continues to expand, then it could be a sign that we're undergoing a geomagnetic excursion, which if that was to continue could translate into a full geomagnetic reversal where the magnetic field actually flips.
Oh, Jesus.
And there's a kind of few ways of tracking that. The three main ways, I guess you could say, would be what's the overall field strength for the Earth? And that needs to drop to a certain level, it seems, for the excursion to really kick off. And right now we're well above that threshold that's been identified, but doesn't mean we can't continue to weaken. The magnetic field has been weakening since our high 1000 AD, about 1,000 years ago. So it's gone down since then, but still historically very strong. But if it continues to weaken, then we have to kind of be mindful of that. But this is like geologic time. It's unlikely to occur within our lifetime. But I also am like, hey, who the heck knows, right? And then there's also where are the actual magnetic poles? Because we have the North and South Pole. But if they start to really move like well outside of their historic areas of, let's say, the Arctic and Antarctic circles, then it's like, okay, we should be mindful of this. And
well, they do move like pretty quick. They move like a couple feet a year. Is that right, Steve? We looked at this recently.
Oh, way faster than that right now.
Oh, really?
Right now, the magnetic pole in the Northern Hemisphere is moving about 40 kilometers per year.
40 kilometers per year?
Yeah.
Whoa.
Yeah, so that's moving really quickly. And there's some ideas as to why, because there's some changing magnetic field dynamics between North America and Siberia, which is interesting. But that is a quick movement. Right now, the magnetic pole in the Northern Hemisphere is almost exactly on top of the actual North Pole. So while it's been moving quickly, it's almost perfectly in the Arctic Circle in terms of its positioning. Whereas the magnetic pole in the Southern Hemisphere, during the same time frame, has moved away from the true South Pole, like the rotation axis, to be just slightly outside of the Antarctic Circle, but it's only moving about 10 kilometers per year, and it's doing it tangent to the Antarctic Circle. Whereas the magnetic pole in the Northern Hemisphere is kind of moving towards the lower latitude zones, like it's moving towards Siberia, it's still off the coast in the Arctic Circle, where there's all the sea ice over Gokul Ridge. But it's starting to, some people are worried about it actually moving into Siberia and then moving down like over India, for example.
The magnetic pole.
Yeah. There's some ideas that, if it accelerates even more, that it could be there pretty quickly. And that, if it accelerated enough, it could. But it's been deaccelerating over the past 10 years roughly.
Okay.
Because it accelerated up to 60 kilometers per year. Now it's down to 40, but still very fast. But the magnetic poles moving are also an indication of what's happening at the magnetic field. And then you can measure specific components of the magnetic field, because you have like a regular bar magnet. It's called a dipole. So there's two poles to it, the north and south. Earth's magnetic field is not exactly a dipole. It's about 95% dipole, but there's these higher order modes. So like a quadrupole, which is interesting because it brings the magnetic field in at the equator as well, not just looping like this from north to south, but a quadrupole actually brings it in at the equator as well. It's 4 lobes. That makes up a good portion of Earth's magnetic field as well. That's a good graphic.
Which one?
That one or the other one in white. But to the right, that one right there. That's a good one as well.
Oh, cool.
And so what happens during excursions is the dipole field strength diminishes greatly and actually goes away. And what we're left with, this is what the evidence suggests, is that then we're left with the quadrupole, the octopoles, the higher order modes, which make up only 5-10% of the overall strength. Those don't seem to change. Then the dipole reemerges in the reverse polarity. And with an excursion, it aborts. So it may get all the way to that flip, but then it reemerges with the polarity it had. Whereas with a full reversal, it will actually take on this new polarity. But that dipole field needs to go away for that to occur. And so then all you're left with is a quadrupole. And that would have really interesting implications in terms of space weather, because now you have the magnetic cusp also not only in the high latitude zones, but also at the equator. So anywhere along the equator, you get blasted with solar energy at that moment in time. Whereas right now it's funneled mostly to the Arctic Circle, the Antarctic Circle. That's why they see crazy aurora up in northern Europe, for example.
Yeah.
Or we don't really get aurora down the South Atlantic anomaly, but we get a lot of those high energy particles because the magnetic field is weak there.
All right, we need to talk about those so-called mushroom gummies you see at all the smoke shops and gas stations around town. Because most of that stuff is no good. It's not mushrooms. It's mystery chemicals dressed up with wizard art. There's a wave of fake Amanita products out there. Some lab tests have even found research chemical tryptamines, benzodiazepines, even synthetic cannabinoids being sold as mushroom gummies. That's why I've always avoided that stuff. If it's behind the counter between a scratch off and a boner pill, I'm out. But here's the thing. Real Amanita muscaria is legal. And when it's legit, it's nothing like the gas station nonsense. And that's why I trust Amintara. These guys are the real deal. They're one of the main importers and processors of actual Amanita muscaria in the country. No synthetics, no secret ingredients, just properly prepared mushroom, ethically sourced and lab tested. I personally use Amanita muscaria as a way to keep from getting too stressed. It's an incredible feeling to be able to remain calm when you have tons of tasks and screaming, fighting kids constantly tugging at you. And it does also leave me with incredible, vivid dreams. So if you're curious about Amanita, don't grab something random off the counter. Use the brand people in this space actually respect. Amintara's 500 milligram capsules and Amanita gummies are consistent and beginner friendly. Just start low and go slow. Go to amintara.com/go/DJ and use the code DJ22 for 22% off your first order. That's AMENTARA/go/DJ and use the code DJ22 for 22% off your first order.
This is a really great graphic. So
does this tie into, this seems like it could be connected to the, what's it called? The Van Allen radiation belts?
Yeah.
So the Van Allen radiation belts are directly tied to the magnetosphere of the Earth and like solar wind, right?
Yeah. So we have our sun, which is, we kind of don't know what it is inside, but we know it's surrounded by this sheath of plasma. super high energy plasma. And then we have our interplanetary environment. So that radiates out from the sun, and we have an overall heliosphere, which is made up of plasma, that the sun is just always pumping out plasma. It creates this larger magnetic field and also this plasmasphere, which we call the heliosphere. Effectively, every magnetic field contains plasma within it. Because if you look at Jupiter, for example, it has a very strong magnetic field. It also has a really powerful plasmasphere. So we don't call them Van Allen belts there. I guess they could be Jupiter's Van Allen belts or Jupiter's radiation belts, but the radiation environment within Jupiter's magnetic field are insane. It's like really, really high.
Really?
Yeah, it's way more intense than Earth.
Why is that?
Jupiter's magnetic field is
Just to have a stronger magnetic field.
It's like 5 or 10 times stronger than Earth's. It's super, super strong. So you get huge amounts. And then you also have, like, for example, here it's showing Io. Io is a volcanic planet. It's blasting stuff into...
Is it a moon?
Yeah. Volcanic moon that's blasting stuff into orbit around Jupiter, which then gets ionized. But every magnetic field effectively also has a plasmasphere. And what happens is that they are particle accelerators. These magnetic fields accelerate particles at speeds near the speed of light. So they go relativistic. And as a result, they contain a tremendous amount of energy, because the faster they travel, the more energy they have if the mass stays the same. And it's not linear. It's like exponential in how that goes up. So, and Jupiter's is actually so powerful that we observe what's known as Jovian flux in our interplanetary environment. So every 13 months, we enter into this arrangement with Jupiter magnetically where we're connected, and we get this burst of Jovian electrons, which we call Jovian flux. And it's a very specific energy spectrum, which is how we identified it to be in Jupiter and not solar in origin. But we orbit around the sun, of course, 12 months. Jupiter does 12 years. And so it's moved 1/12 of its distance in 1 year. So that's why it's 13 months. Because as we orbit around, it's moved 1/12. So we need another month to catch up to that magnetic configuration. But we see particle acceleration with Jupiter and massive amounts of radiation there. And we have that here on Earth too with our radiation belts. And so our magnetic field is also accelerating these particles, and it's being fed and replenished all the time by these solar storm impacts or solar wind that connects to Earth in a preferential way, like a conducive way, will recharge our plasmasphere. And then that plasma often will precipitate down into our planet and drive these geomagnetic storms. So it's a really complex system.
Yeah.
It gets wild, because then how does that affect the telluric currents, and how does that affect maybe the geodynamo, and at what time scale are you considering? Is it just the hourly, daily time scale, or you think how does maybe space weather affect the geodynamo over thousands of years? These are all open questions in many ways.
Getting back to what you were just explaining about the North Magnetic Pole shifting down into Siberia or like India, what would happen if that happened?
Well, the main thing to be aware of as it relates to the movement of the magnetic poles is that if Earth's, so I'm sure that there's a wide range of possibility that's happened over Earth's geologic time frame. We have quite limited data on that. In terms of modern data, it's almost non-existent compared to the geologic time frame. So in general, though, if the magnetic poles were to move well outside their normal ranges, then that's an indication that the field strength is diminishing, and that magnetic pole really doesn't become that great of a measure of what's happening anymore, because the overall field is weakening in general. The dipole field is going away. So you're going to have a lot of places where you could say the magnetic field is going in vertically. Like there'll probably be multiple magnetic poles that could pop up. But when the dipole field is strong, you have two clear magnetic cusps and two clear places where the magnetic field is going in vertically to the Earth.
I see.
But as the magnetic field diminishes, that can kind of just get thrown into flux. So it's a useful measure, but in some aspect, if we're really undergoing an excursion, it kind of becomes less useful because they can really float around really quickly because the whole field itself is so chaotic and turbulent. Like the sun undergoes a magnetic flip about every 12 years. That's the solar cycle. And during that time, there's tons of places on the sun where the magnetic field is kind of slicing back in and
Oh,
There's gonna be
really? So it
multiple
wouldn't
magnetic
make it.
poles.
It wouldn't really affect it. We wouldn't really notice it.
I mean, we would definitely be able to track this and it would affect us, but it's not the, I guess what I'm getting at is it's not the best way to track what's happening with the magnetic field, like just the location of these magnetic cusps. It's not the best way. I think probably better is to track the dipole to quadrupole ratio, and then
Yeah.
also the overall field strength. But as that pole moves, you're going to have energy flux moving with that cusp. So one interesting thing I've talked about, and this is, speculative, but we have evidence of there being a supervolcano in the Arctic. This is the slowest part of the Mid-Atlantic Ridge is called Gokul Ridge, and it cuts from effectively Svalbard up to the Arctic Ocean. And at the very end of Gokul Ridge, there is a giant caldera that's been identified. It was first identified in 1999. And it's huge. It's like this massive depression in the seafloor there. And this is oceanic crust that's already thin. And normal mid-ocean ridge where the plates are being generated are spreading apart pretty quick, 2-4 centimeters per year. At Gokul Ridge, it's like 1 centimeter per year. And at the bottom of Gokul Caldera, it's like 0.6 centimeters per year. It's like 6 millimeters per year. So it's super slow. The best idea of what generated this huge caldera, like 40 kilometers across, 80 kilometers wide, roughly, somewhere in that zone, 1.2 kilometers deep, is a giant supervolcano eruption. And the dating evidence goes back to about 1.1 million years that there was a massive supervolcano event that ejected about 3,000 cubic kilometers of material, dry rock equivalent. And Yellowstone was like, last time it really had a big one, was 1,000 cubic kilometers. So this is up there with some of the biggest volcanic eruptions ever observed. Toba would be another huge one.
Whoa.
But right now, the magnetic field in the northern hemisphere, that cusp, because that's where the field's going vertically in. So the energy flows down those field lines. Like these particles are guided by the field lines. If you have a neutral particle, it's not affected by magnetic fields, because it's neutral. So
Right.
if it's like a neutron, will just go out in a straight line. But the moment it takes on charge, the magnetic field is so much of a stronger force than gravity, it will guide the flow of that particle. So right now we have the magnetic pole moving over Gokul Ridge. And if there is still a supervolcano system there, which there's evidence that there is, we just had a huge burst of seismic activity there in 1999, and 3 new volcanoes were generated that created pyroclastic flows under the ocean. Like they retrieve pyroclastic glass at depth, which is insane to think about. And the fact that Gokul Ridge is still super slow in its spread, that seems to be how some of that energy gets released, rather than it just being purely through the spreading of the tectonic plates, that some of it accumulates in these underground magma reservoirs and then explosively releases. And they sampled these samples from that volcanic event that occurred in 1999, shows that the CO2 ratio is like super enhanced compared to normal. It's like 13.5% versus normal like 1.5%. So when that finally depressurizes, it's super explosive, way more than normal. So I mean,
That's fucking crazy.
it's a whole rabbit hole. But we've seen the magnetic pole circle through the Arctic quite a few times now. That's just in the past 2,000 years. It's done loops through the Arctic. That's what the some of these lake bed sediment cores show, is that it just kind of like circles through the Arctic. But what does the magnetic pole moving over this massive energy reservoir, magma reservoir, do? Because you're having more high energy flux come in. Now, a lot of that's going to interact at the atmosphere level, but now you're generating electric currents, these telluric currents that then induce down into the ocean, they induce down into the surface. And I just think that there's probably a reason why one of the biggest supervolcanoes that we've identified on Earth is right where the magnetic pole normally hangs out. Doesn't mean we're going to have it explode when it crosses over in like the next 10 years, but it's certainly just interesting to think about.
What is is there any like consensus on when this supervolcano last erupted?
Yeah, about 1.1 million years ago.
1.1 million years ago.
Yeah, so the last big eruption, there's really not that much research that's been done on it because it's all fairly new. And yeah, so it's good to take a step back and to, not get carried away with things. But
Yeah.
it's just one of these examples I think that you can look at to maybe better understand the space to Earth connection. Because we have a ton of data showing how certain flows of plasma in our magnetic field, the plasmasphere, further out in space, like the radiation belts,
Yeah.
influences telluric currents actually flowing through the surface.
Yeah, that's interesting. I'm new to this, but like just the term space weather seems so bizarre. Like, how can there be weather in the void of space?
Well, that was the thing. Back in the 1940s and 50s, they thought space was a void.
Yeah.
They didn't really think that there was plasma flying around. And they thought that when the sun had a big solar flare and launched out a solar storm, we all of a sudden went from a void to a big, impact of plasma. But what we found out the moment we put probes out there is that there's always plasma in the interplanetary environment, and therefore there's the solar wind and interplanetary magnetic field. But there can be big changes. Sometimes it does become almost a complete void. And weird things happen to the Earth when we go through those patches of super, super, super low density solar wind. A good example is that right around the time, like, I'm talking like weeks or months here, I'm talking like days to hours with the magnitude 9.1 Great Tohoku earthquake, March 11th of 2011, Japan. We had a super big drop in the solar wind density, like an anomalous drop. And then we had that earthquake go off. So, and there's other connections there too. There's other big earthquakes that have lined up with these huge decreases in the solar wind density. Not every time, but it's just kind of coincidental that that's happened in more than once.
So what contributes to more or less solar wind density?
If you get a big solar storm to launch, that will create a spike in the density because it literally creates like a shock wave, like that EMP you talked about.
Yeah.
Right, that'll hit. And what happens if it's fast enough, or some of these solar wind structures that can exist, like these high-speed streams, is it'll sweep up plasma in front of it because it's traveling very fast. Let's say it's traveling 1,200 kilometers per second. And the regular solar wind is 400 kilometers per second.
Okay.
So it'll sweep all this stuff up, and then there'll be the actual bulk of the plasma behind it. But then behind that will just be basically nothing until a new solar wind structure sweeps by and replenishes that part of the interplanetary space with plasma. So with really big storms or some of these special solar wind structures, like high-speed streams, you can have these huge gaps in the solar wind density.
Right.
And sometimes we don't know why they occur. Like there's been
So behind, at the back end of these solar storms that come through, there's like a void of very low density solar wind. And somehow that equals more volcanoes and earthquakes.
Yeah, there's that the solar storm dynamic that often seems to play out. The strongest connection between space weather and earthquakes seems to be for these more structured solar wind dynamics, where they're called these high-speed streams, and those seem to be better correlated with earthquakes rather than sometimes just these big solar storm impacts. But either way, there's too many odd things that occur if you keep track of this. If you keep track of all the different things, the space weather, the earthquakes, the volcanic activity, there seems to be not coordinated pulses, but there's definitely like pulses of activity, and then there's periods of quiescence, and it's not necessarily just homogeneous and completely random. And often when there's a big space weather impact coming in, we also happen to see like a clustering of high magnitude earthquakes. And then we often see that occur also with planetary alignments and such. So
Yeah.
it gets kind of wild, but I think this is just us coming to a better understanding of how all these factors play together and in ways that we may not really know yet.
Well, the sun is like burping and belching all the time, right?
Yeah. Except during solar minimum, when it's pretty quiet and happy.
Yeah.
And we go through long minimums. Like sometimes we'll have these grand minimums that last 50, 100 years. They can last a long time.
And so what sort of tools are people like you using to detect or predict these solar storms or things like this? Are you just looking at the sun and you can predict it by just looking at the sun and what happens with the sun, like ejections or solar flares or whatever? Does it all come from the sun?
Well, so Miyake events, if you go back to super flares and, these records of Miyake events, the researcher's name was Miyake, which is why they're called that. She first detected these huge radioisotope spikes in tree rings, looking at trees and such. They've detected a whole bunch of them now. We don't know 100% whether those are solar or cosmic in origin.
Right.
They could be cosmic.
Oh, coming from other systems.
Somewhere. A lot, if you look at the cosmological environment, a lot of plasma gets focused into jets. We have these astrophysical jets across a variety of scales. So we see sometimes at the center of galaxies, they emit these jets of plasma outwards, traveling super fast. We see with gamma ray burst, where it's actual light photons at the highest frequency, gamma rays. Sometimes those come focused in jets and impact the Earth. Like we had the largest gamma ray burst ever detected back in October of 2022. The research is indicating that was a very focused jet of gamma rays that hit us from 2-point-something billion years away.
Whoa.
Billion light years away. So we see this sort of jet activity exists in our astronomical environment across different scales, galactic, interstellar, etc. And so it is possible that if some, let's say, nearby supernova occurred and it was lined up in such a way that it shot its jet out at us, when that hit, that could also create a Miyake event. Those are the two main ideas. It could be super flare, some sort of cosmic event where you have it's from outside our star system, but still significant enough to cause this massive increase in radioisotopes and energy and more. Then I also think that there's a possibility it could come from within the Earth itself, though I don't know how that would occur.
Sure.
But I don't think we can just say that it's not a possibility.
That makes sense.
Those are the three main things: sun, Earth, or cosmos.
Okay.
And maybe it's a convergence of all three. Like we see with these geomagnetic excursions that they seem to be correlated in time with the sun undergoing a period like multiple grand solar minimums. So there seems to be this coherence, you could say, and this resonance between the sun and the Earth. And when the sun is undergoing these periods with very low activity, that's when Earth's magnetic field decides to flip.
Got it.
At least that's what the recent data suggests for like the Lechamp excursion, where they looking at radioisotope data. But the thing is,
what's up with all the fear, like all the crazy hypotheses and theories I hear online about like the pole flip could reset humanity?
Yeah.
Like everyone says that this could be like a cataclysm.
Yeah. So during an excursion, so like the Lechamp excursion, the field strength went down to like 5% of what it is now for about 100 years, roughly. That's about the time frame and about the field strength. And that would mean that if you're out and about, you're receiving a huge amount of cosmic radiation. And that's not going to be good. Also, if there is this connection between grand solar minimums and geomagnetic excursions, during a grand solar minimum, you're not getting these big super flares or solar storms or whatever, just solar flares in general, but still pumping out most of its energy, which is most of the irradiation from the sun is infrared, visible, and then also ultraviolet.
Right.
And ultraviolet, can break DNA bonds and, single strand breaks, double strand breaks, mutations, all that. So if you had a geomagnetic excursion like the Lechamp, which is when the Neanderthals died out, and the field strength's at 5%, you're letting in a ton more cosmic radiation. The sun is still pelting you with UV light as well. So it's going to be fairly traumatic. We had a megafauna extinction in Australia at that time. Big animals can't hide from this stuff. Whereas
When are we talking again?
this is about 42,000 years ago.
Oh, okay.
42, 44,000. It's roughly in that zone. I think that is why those cave systems in Turkey exist, if you're aware of those.
You're talking about the cave they found underneath that house?
I'm not sure about the house, but they have this elaborate cave system in Turkey that's thousands of years old. I don't remember the specific name.
So you can find it, Steve.
Yeah. But a lot of people have different ideas as to why that exists. But if you have a geomagnetic excursion, the cosmic ray, like you can feel this stuff, right? When the sun's really active and you go out, or just going from, let's say, Nebraska down to Mexico, you're like, wow, I can really feel the sun on my skin.
Darren Kuyu? Talking about Darren Kuyu? Darren Kuyu is the one they found under that house. They dug under the house and they found this giant cave system.
It was like a giant man-made anthill.
Yeah, exactly.
Yeah, that's
Is that what you're talking about?
Yeah.
Okay.
And so I think that could exist specifically during these sort of events where you would literally feel the energy hitting you and it would not be pleasant. And over time, you would see health effects from that. And so it makes sense that you would take shelter underground.
Right.
And this is a long period of time too.
How long do you think?
It's like 100 years. And that's just where it's at its absolute minimum for the field strength. It's going to be about 1,000 years of where the field's very weak. So it's a long enough time for that to make sense. Whereas some of the ideas that people have is that it's a big solar storm, like a super flare coming in, and they run to the caves. But that's like a 3-day thing. And you don't have a heads up on that. It's not something that okay, this is clearly a factor. Let's work around it.
So when you're saying this could have lasted 100 years, what you're saying is it could have been different day to day. There could be days where it was safe to walk around. This wasn't just a consistent 100-year period of super intense radiation hitting the earth.
No,
right?
It would be.
Oh, it would be constant.
In general, yeah.
Okay.
Yeah. I mean, it's hard to say without being there and getting the data. But
sure. I mean, we're speculating wildly, but
in general, for the Lechop excursion, we see that the field strength dramatically weakened. And so that would be factored. Same amount of UV light if you did have all these grand solar minimums.
Yeah.
And then a ton more cosmic radiation, which is going to cause mutations and more. So something like that makes perfect sense. And it's a long enough time period for that to be a feasible engineering project that makes sense to devote resources to. It's not just why would you have that for a super flare you don't even know is coming? Yeah,
well, I never understood. I've heard the explanations that these things were to protect people against floods. But why would you want an underground cave if you're getting flooded, right? I never really understood that. And they claim that the rock doors could have blocked the water, but I don't know if I buy that. I don't understand how this underground Darren Kuyu, how you could survive underneath that when there's tons of flood water surging above you. It would just go down there, I would think.
I mean, I haven't been there. I like to go to these sites so I can speak about them.
This is not accurate. I don't think this is accurate, Steve. I don't think that's what it looks like.
Oh, yeah, that's Cappadocia.
Oh, okay. Yeah, something different. That's volcanic caves, also in Turkey? Whoa. Christian churches inside these caves? Huh.
Tuff, yeah, volcanic tuff is easy to carve out.
Yeah.
So that makes sense.
Hold that thought. I got to take a leak real quick. We'll be right back. There's so many possibilities for what could have caused extinction events in the past. Is it comets? Is it volcanoes? Is it solar flares? Is it all of the above? Who knows? But it's fun to speculate. They're some of these structures. This had to have been why else would they dig these underground cities unless it was to escape something, right? And also to live without sunlight for an extended period of time has got to be super unhealthy. You would imagine that there wouldn't be long-term health effects living underground.
There has to be some health reason that outweighs that, I would think.
Exactly.
I don't think it's climate.
That's a very, very well stated.
I don't think it's climate because, it gets hot there, but we don't see people in Turkey living in these underground cave systems right now.
No.
So, and actually back 5, 6, 7,000 years ago, it was probably quite a bit nicer there, right?
Really?
Well, I mean, you had back during the Ice Age, Turkey was probably a great place to live because it was quite a bit colder. It's still a very nice place, but it gets hot there during the summer, or like Egypt, for example. But 6,000 years ago, Sahara was still green.
Right.
So in terms of it being like absolute scorching desert, and that's people go there to live in cooler conditions, I mean, maybe. I think it's probably doing multiple things at once.
Have you ever seen those? A couple years ago, we had Randall Carlson in here showing us this graph of all of the ups and downs the climate has been through for millennia, and it's like there's these insane. He was using it to illustrate like the Younger Dryas, the time period of the Younger Dryas, how like we went from super cold to super hot, and there was these huge spikes like at the beginning, at the end of the Younger Dryas, and all this stuff, and like how the temperature has been just up and down forever. And he was showing like during, I believe, I mean, it's been a while. I don't know if this is, I'm recalling it correctly, but I believe he was showing like during the medieval period, it was like super warm, like even warmer than it is now. Are you familiar with this?
Yeah, the medieval warm period.
Right.
Yeah.
And how much, do you know how much warmer it was like than it is now? See, you can find that graph, Steve.
It was not
Super
homogeneous. So a lot of the warming was concentrated in places like Iceland, Northern Europe, Greenland. It was much warmer there, like much warmer than it is in the current day. That's why it was easy for them to go and settle those locations. So it wasn't the warming was really concentrated in some of these high latitude zones. It was not homogeneous around the planet, but there was a distinct warming event. Interesting work that was, and some connections put forward by my buddy Max Raymond. I have a podcast with him on my channel, but he looked at the record of supernova explosions and also the medieval warm period. And there's like a pretty tight correlation in time between us seeing these supernovas, which if we're seeing it, we're getting some energy from that. Just how much, what type, what's the significance, it's hard to say.
Right.
But there is this connection in time because we had 3 big supernovas that we saw at the early, I guess, 10th, 11th, 12th, 13th century. Like the famous one's 1054 AD. But then we see this distinct warming that occurred immediately after that. But I mean, there's records of that from the Chinese, the Japanese, across the board. But effectively, I mean, that's the Crab Nebula that was formed. But that was such a bright and powerful supernova explosion that it was like immediately one of the brightest things in the sky for months. So, I mean, a huge event. And it didn't occur that far away, right? There's supernovas that occur in other galaxies, and nowadays we can detect them. But for us to see it, it's going to be, it's got to be fairly close to us. And he's connected these repetitious nova or supernova events to, I think they're called like Dansberg-Oersgard cycles, these random swings in the climate. I'm sure when you were with Randall, you're probably talking about those because you sometimes see these dramatic leaps up in the temperature of the Earth based off of the records from Greenland and ice core stuff.
Right.
That do not line up with Milankovitch orbital cycles and resonances. So the question is like, what's creating like this massive sudden 2-degree increase in global temperature? And you can look at some of these supernovas and these nebula have multiple rings to them. And so the velocity of the expansion, then you also know the distance. That's also an equation that you kind of need to figure out is how far away they are.
Right.
But you've put those two together, you can get a sense of when the explosion occurred or explosions in time. And so Max, my buddy Max, he lined them up. He's like, this is kind of interesting. Like they line up in time with these sudden warming events.
Interesting.
So, I mean, you can't, I wouldn't like stand on top of the hill and, tell everyone that's 100% the case. But
Go to that one on the left, Steve, where it has the actual, that one. Click on that one.
But I think we should be thinking about our environment here on Earth in a more interplanetary and interstellar sense. I think those outside forces and the environment that we're in matters a lot more than we currently think.
What do you mean by that?
I think our star and also our surrounding cosmos has a much more direct impact on the Earth and therefore like our living conditions than we may think initially think. If the younger dryas was caused by comet impact, like some of these things are fairly, you can kind of get a sense for them, like a giant comet coming in and impacting. We've seen this in the movies, but if this supernova connection or even novas that are strong enough and they have their jets aligned with us, if that has an impact on the Earth, that's a little bit less tangible, but I think we should consider these things.
Yeah, totally. This is an interesting graph. I've never seen this one before. So from 100 AD, or from like 0 to 100 AD was the Roman warm period. So it looks like it was about a degree warmer, maybe Celsius, than the Dark Ages, which was from, it's a little bit off there, but it's from basically like 300 to 1,000. And so is that right? It's saying it's 1 degree cooler from 8 to 9?
I'm guessing.
Okay.
Yeah, we go through these oscillations.
That's wild.
But 1 degree globally is a big, like,
what?
It's a big, is this global? Because if it's global, then it's
it doesn't. I don't think it specifies if it's global, but I can't imagine 1 degree would make much of a difference.
It depends, and again, these warm periods are not homogeneous in nature. So it's not that the entire Earth experiences the warming or cooling uniformly. It's
specific pockets of the Earth.
Yeah, yeah.
It's interesting though that the medieval warm period seems to be even warmer by maybe a ½ degree than the Roman warm period. Because the medieval period is so interesting because that's when human beings like created like the most incredible like architecture and stuff like that over in Europe. And, you have like more art and architecture and crazy stuff. But also, I'd be curious to see what the temperature was like even in the classical period. I don't know if we have any. I'm sure we have a ways of determining that. See what that was. Let's see what the
classic ancient Greece.
Yeah.
500 BC.
Yeah. Like the classical period all around like the Near East and that part of the world.
Yeah, it doesn't go far enough back.
Huh. I wonder why.
I've seen some graphs though. I mean,
and we're in a cooling period now, right?
Well, overall the Earth is warming. But in general, I think the safest thing that you could say is that our climate and weather is becoming more volatile. So we're seeing...
Really?
Yeah. I mean, for example, in December, there was a huge heat anomaly over the United States, though like the Yukon, Canada, Alaska, that was excluded. They had a huge cold snap there. Also, like Maine was quite a bit cold. But like here and also Texas and a lot of the heartland, the U.S., had tons of temperature records broken for December. Meanwhile, Moscow, like right now, has had one of the biggest like polar blizzard cyclones of all time. And the snow is piled up like crazy. So overall global temperatures are going up. The Arctic is warming like 3-4 times faster than other spots. But in general, there's just more volatility across the board. That's my take home, because what we see is sometimes we get these sudden changes in temperature. So like we could be on this warming, but I wouldn't be surprised if all of a sudden we have a cold snap that comes in, because we're in an interglacial right now. That doesn't seem to be the trend, but trends sometimes suddenly reverse. But if we want to be prepared for the future and just kind of understand where we're going, then the bigger thing to be aware of in my mind is that we're just seeing increased volatility, stronger storms, more frequent, in locations that we typically wouldn't have storms, at least with our recent record. I guess one of the big things I really want people to be mindful of is that a lot of our data doesn't go back that far. I mean, let's say like 1850, right? For a lot of climate records, a lot of our geologic records, like the solar records. I mean, the space age started in like the 50s. So a lot of that space data only goes back to like 1950, really. So we have in our seismic data for earthquakes, we have some data going further back because we found the fault trace in the slip and we can reconstruct it. But in terms of like good seismic data, like 1900, these data sets are almost meaningless in a geologic sense. I mean, they're super useful and we get good information out of them, but 10,000 years of data or 50,000 years of data, that's still just a drop in the bucket for the Earth, which is millions and millions and millions, billions of years old. So I think it's important not to draw too many definitive conclusions as to these are the only possibilities that exist for the Earth.
One of the craziest things to me is it's so hard to know what's really going on with the Earth's climate and and all this whole topic. It's so hard to know what's going on because it's like it comes with so much political baggage.
Yeah,
like there's nobody who has a take on the climate that is not attached to their political ideology or like what they label themselves out.
Except maybe me.
Yeah, right.
That's because I see it. My first principle is I want to understand what's happening. So, and well, politics, I mean, the whole thing's stupid. So like I could care less about either side, but I just want to understand what's happening. So we know that like our sun, the star in our system is the main driver of climate. Because if that was all of a sudden to go away, Earth would all of a sudden be very cold, dark. It would not be a fun place, right? It would change everything. We're close to the sun. We receive a lot of light radiation from the sun. That's our total solar radiance. It's about 1,370 watts per square meter of energy coming in. That changes across the solar cycle. Total solar radiance doesn't change that much. We can say it goes from like 1,370 to 1,374 in terms of total solar radiance because most of that energy is infrared, optical, or visual light, and then also UV.
Right.
But we get distinct changes in X-ray light, extreme ultraviolet light. Also, radio frequency light goes up quite a bit in intensity during solar maximum versus solar minimum. But that's the main driver of the climate. Then there's what's happening with the Earth and her own changes, let's say like water vapor in the atmosphere and the hydrological cycle. And then there's what are we doing to alter those systems with anthropogenic greenhouse gases and stuff. And for some reason, some people are like, oh, it's just CO2 and our sun doesn't affect the climate at all. And then other people are like, oh, CO2 does nothing. It's just the sun. It's like, it's a combination of all these factors.
Right.
And they're probably going to vary in their significance at times too.
Sure. Of course, we contribute to the carbon in the atmosphere, like the CO2. Of course we contribute to it. Is it enough to literally like create a new ice age? Or not a new ice age, but like to warm up the Earth and melt the ice caps to where like it's going to change the Earth? Like I don't know. But it's just, like I said, it's just so volatile and there's no middle ground in this kind of stuff. And it's hard to like hear a nuanced take on what's really happening. I see articles all the time that the ice caps are growing, right? Like the ice sheets are getting bigger right now. And, depending on what website you go to, you can find a different scientific take on what's happening.
Well, yeah, I mean, December would be a good example because some outlets were probably reporting about the huge cold snap that hit the Yukon and parts of the U.S. Meanwhile, other outlets would only cover the huge warming trend that hit, the heartland and most of the United States. And,
right.
Europe's a whole different place, but other parts of the globe. But yeah, it's unfortunate that...
Look at this. NASA satellites show Antarctica has gained ice despite rising global temperatures. How is that possible? An abrupt change in Antarctica has caused the continent to gain ice, but this increase documented in NASA satellite data is a temporary anomaly rather than an indication that global warming has reversed, scientists say. Yeah.
Yeah, oceanic circulation.
The problem with all this shit is that it's just so entangled with money.
Yeah.
There's all these little financial entanglements in science that make it screwy, which sucks. It's with everything.
Yeah, money's kind of a crazy thing, which is, I'm not perfect. And, I've made mistakes, and I'm sure in 10 years I'll look back at certain things I've said or thoughts I had, and as new data comes out, I'll be like, okay, this is my new revised idea on this. But I do like the fact that I've taken myself out of any kind of constricting influence by just kind of becoming independent, and by educating others publicly online, people like that enough that it keeps me afloat. And great. I think we need more independent voices. I think we need more independent data collection networks. Like, one of my long-term life goals at this moment in time is to create like a global observatory for geophysical and solar data and more. So we're not reliant just on government organizations. Like, one of your questions earlier is where do I track this stuff? And we get a lot of great data feeds from NASA and NOAA and other space and government organizations. But there's often political interest there and conflicts of interest. And I mean, there's some things that just sometimes you're like, why are they not speaking the truth about this? Or why are they not addressing this thing that occurred?
Why are they assassinating plasma physicists?
Weird stuff, dude. Yeah, the MIT.
Dude, how crazy is that? I saw some stories about that. I don't know what to think. There's just so many crazy takes on that MIT guy. He was an MIT plasma physicist, right? Yeah,
Italian guy. And I think he was like 43, 44.
And he was on the cusp of he had recently cracked something, I heard.
So he was, I don't know the full story, but he was the director of plasma and fusion science at MIT.
Right, plasma and fusion.
And he was specifically looking into understanding turbulence in fusion reactors. Because plasma is really interesting. It's the fourth state of matter. It's the most energetic form of matter because it's highly ionized. And therefore, you're playing with a lot more electromagnetism than you are with solids, liquids, or gases. And plasma doesn't really like to cooperate or behave. So the whole nuclear fusion discussion is interesting because when you create plasma, it often likes to bend back in on itself and undergo these instabilities, and it doesn't really like to cooperate. And so with a fusion reactor, they're effectively creating this plasma. They want to condense it down to a point where there's such a high concentration and density of these ions, like hydrogen, that they eventually do run into each other and then, fuse to form a helium. But if you can't get the thing to condense down in the first place, you're not going to have success with your fusion reactor.
Yeah.
And so plasma seems to resist these dynamics. And so you need really powerful magnetic fields to confine it. But plasma is also generating its own magnetic fields, and so you create all this turbulence. So again, I don't know this guy's full life work, but he was specifically looking into plasma turbulence. And that would be a very important thing to understand as it relates to fusion and being successful with that. And I read something about it being like a personal vendetta, the guy who murdered him. But dude, I don't believe anything nowadays. After the whole, especially like with that Boeing whistleblower situation, and then the guy gets whacked, or I just saw this.
There was multiple guys who got whacked with the Boeing thing, wasn't there? Like a bunch of key witnesses that were getting ready to do depositions, and the day before they died.
I think it's more than one, yeah.
Yeah.
And then also, I don't know, but this guy just released a YouTube video that he cracked the Coca-Cola recipe.
I saw that.
Reverse engineered it. I'm like, dude, what? I would be worried if I were you because.
That's funny.
Really though.
Coca-Cola is going to send out their assassins.
It's kind of tongue in cheek, but after you just see when there's big money and big interest and there's monopolies and such, you got to be kind of mindful of these things. So
yeah, the plasma stuff's super interesting because you don't really learn about plasma in school, do you? You kind of learn about all the other states of matter, but the plasma one's the weird one. Because it's true that 99% of the universe is made of plasma.
That's what they say. Yeah. Our space environment is a mix of plasma and then also neutral gas. But it's interesting. 99.9% would be because most of the mass is contained within stars, and stars are highly energetic, so they're plasma.
Right.
But when you talk to a lot of astronomers or just listen to what they say, often they're not talking about plasma. They're talking about gas, they're talking about dust, but for some
Dark
reason,
matter.
yeah, and these made up things which we don't have evidence for, dark energy, dark matter. Like they're creating new variables to fill in their theory and their equation, which probably is broken to begin with.
Sure.
That's my thought, at least. I think we'll have a paradigm shift in our understanding of some of these things cosmologically in the next 5, 10, 20 years. I don't think dark matter, dark energy will survive. I don't think I don't think Big Bang will survive. I'm not an expert, like end all be, but I think sometimes we get too entrenched with our ideas, and there's other explanations that were put forth at the time, matter antimatter balance, that would explain a lot of these things more elegantly, but because maybe someone has personal beef with someone else, it doesn't take off. And these dynamics exist in life. But yeah, 99.9% of the universe is plasma. We don't really understand it. People don't really talk about it. Like, is it just in space? Is it also here on Earth? We see with earthquakes, especially land-based ones, sometimes these earthquake lights.
Oh, yeah. Those are wild, huh?
Yeah, really cool. We don't have that much footage of them because we need it to be at night. It needs to be a big enough earthquake. It needs to be a land-based earthquake. But sometimes, like in New Zealand, I think it was 2017, 2018. It's like a big magnitude 7 something. We see these, flashes of green, blue light coming up.
They often get mistaken for like UFOs too. There's Marfa, Texas. I think there's a lot of these earthquake lights that come out of the ground. There's something. What is it about Marfa, Texas, that makes it super conducive for all these earthquake lights? It might just because there's lots of like underground seismic activity. There's this NASA physicist, I believe retired now, named Friedman Freund.
That guy's great.
Yeah, you're familiar with him? Yeah, so he's the one. He came up with this hypothesis that the igneous rock underneath the Earth, when it grinds together, because it has this charge in the igneous rock, and when it grinds together, it somehow produces enough energy to shoot these earthquake lights out of the ground. And he came up with the idea of using that as like a early warning detection for earthquakes, right?
Yeah, his big thing was, if we zoom out, was really understanding electric circuits in the subsurface. And so what he called rock circuits. And he did a lot of laboratory testing and then also looking at observational data. But when you put certain rock types under mechanical strain, they generate all of a sudden electric charge. Now flow in a circuit. And a circuit is bounded by the conductivity of the materials. So if you can all of a sudden increase the conductivity of some of the circuit pathway, that will increase the energy flow dramatically if that potential energy exists. And so one key example that he pointed out was this earthquake that struck San Jose, the Bay Area, South Bay, from the Calaveras Fault in 2005, I believed. I think it was a magnitude 5.1. Is that or 5.5? Either way, not the biggest earthquake, but they noticed in the hour, and that's where he was based off of the NASA Ames centers right there in the South Bay.
Yep.
So he had access to all this data. There's a widespread network of conductivity sensors, atmospheric conductivity sensors across the South Bay. And before that earthquake occurred, all the sensors in that area went up to their highest value and then went offline. So the atmospheric conductivity went up dramatically. We don't know how high because it went off the capability of the sensor to read, and then the earthquake occurred.
Whoa.
So his idea was that there was a huge ionization event that came up from the subsurface that was able to increase the electrical conductivity of where we live, the boundary layer in the troposphere, which is very resistive, right? It's the very dense atmosphere where we are at the surface, but very low conductivity. If that can all of a sudden become conductive, now you have a really strong ability to close a circuit across a vast distance, because you can connect one place of the Earth to another. And if there are electric circuit dynamics involved with earthquakes, which, I mean, that's 100% where I am based off my research, and the earthquake lights are great. Observational data supports that. Then that could be a dynamic at play. And so the conductivity sensors all went crazy and then totally, topped out, and then boom, magnitude 5.1 earthquake, and then they cooled back down afterwards. But that's not even that big of an earthquake. There's Loma Prieta, magnitude 6.9, 1989. They happened to put a magnetic field sensor in the Santa Cruz Mountains, I think just about 7 miles away from the epicenter, which is, the surface directly above the hypocenter.
Yeah.
And they noticed these magnetic field fluctuations across a variety of frequencies leading up to the Loma Prieta quake. So this is like Schumann resonance frequencies, which are like 0 to 50 hertz. This is extremely low frequencies, even lower than that, like 0.01 to 1 hertz. Magnetic field fluctuations. So the Earth is way more complex and interconnected. The 1964, the Great Alaskan Earthquake, magnitude 9.2. The founder of the company I used to work for, his name was Sheldon Briner. This is Geometrics. He was a maverick. He actually was the guy who discovered the Olmec heads.
What?
No
way.
Yeah. So by horseback, he had a magnetometer, and the Mexicans knew roughly where they were.
Yeah.
But they were buried down quite a bit. So he went out there, and being in California, it's not that far away, and he did these magnetic field surveys, and he found the anomalies associated with the Olmec heads. They dug them up, and unfortunately, not that many people know about him, but he then started to get into some really interesting fields in terms of like the connection between magnetic fields and magnetosomes and Alzheimer's and all this stuff. I met him just like a couple months before he passed away in November 2019, because he showed up for the 50-year reunion for Geometrics, the anniversary. And he was in great health then. Anyways.
What was his name?
Sheldon Briner.
Sheldon Briner.
Yeah, Breiner. Yeah, really interesting guy. A lot of cool research he's done. I look to him as a bit of a guiding light.
Mm-hmm.
He had, he was basically at the front line of magnetometer technology back in the 50s and 60s. And yeah, there's a photo with him in the Olmec heads as well.
Oh, wow. Look at that. That's bizarre.
Yeah. And so he had a magnetometer set up in Portola Valley where he lived, and he noticed these long period significant magnetic fluctuations that occurred with the 1964 Alaska earthquake. He was also picking up on his magnetometer all the nuclear testing that they were doing in Nevada when that was all still basically top secret. He like checking his data. He's like, what the heck was this magnetic pulse right here? Like, this is strange. It's like, oh, actually, they're doing nuclear testing nearby.
Right. Not only that, we were detonating nukes in the atmosphere, in like outer space.
Yeah. I think that's Starfish Prime, if I recall correctly.
They're trying to blow a hole in the Van Allen belts or something.
If you look into the geophysical observations done around all the nuclear testing, it's really insane. Because what happens is you have this, fissile material. Eventually, they move to fusion bombs, but you have this fissile material, and you're immediately creating a shock wave of plasma afterwards, but you're also generating all these bunch of particle flux, a lot of them being neutrons. And so these neutrons are not affected by magnetic fields. They fly straight out, but they decay into a variety of other particles. The main one that we're interested in would be electrons. So you have this explosion, then the neutrons fly out, and the moment it decays into an electron, with the other stuff too, but the electron is now governed by the magnetic field, and the magnetic field connects one part of the planet to the other. So there's these conjugate magnetic points that exist, and so the electrons can then flow from that location to the other side. And so they noticed with a lot of these nuclear testing and these blasts that were done, that all of a sudden there'd be aurora on the other side of the planet, and they were trying to figure out why. And so the idea is this particle cascade dynamic.
Whoa.
And though neutrons decay quickly, there's enough of them that do probabilistically get out far enough to then deposit their electrons, the stream of electrons, in certain orbital levels that then will feed back to that complete other side of the planet. So we were really basically messing around with the Earth in a big way, back with all the nuclear testing. I don't think those energetic effects have wrapped up. I think that's still working its way through our Earth energy system, you could say, but not too much research has been done on that now. And there's also a bit of amnesia there. And I think there's also some cover-ups that have been done and such, but some really crazy dynamics existed. And he was tracking this all back in the day, and he had an open mind. So when he saw this, people had much more open minds back in the 50s, 60s, 70s. That's my impression, reading the research and talking to some of these people.
Now, I heard you talk about this guy named Hans Alfven or something like this. He was like a plasma scientist.
Yeah.
What was it? So is he still alive?
Fortunately, no. I've thought about how if they trained some like AI model on him, how that would be nice. But of course, it wouldn't actually be him. But he was a very open-minded astrophysicist, and he was really against the Big Bang, and very, if you read into his books, you get a sense of the history of astronomy and astrophysics, and that helps you understand where we are now. Because back in the day, and still to this day, they had a lot of ideas and theories, but they weren't built off of observations. And then we started sending probes into space and actually collecting data, which then disproved a lot of these ideas. For example, the vacuum of space.
Right.
They thought Earth's magnetic field was shaped a certain way. It's just basically a very simple dipole magnetic field because there's nothing to influence it. Then we actually sent, probes out into space, and we realized that the magnetic field is more like a teardrop. It has the magnetotail behind it, and there's all these structures, the magnetopods, and it's very complex. Depending on the solar wind dynamic, it can change. Like, it's not a simple dipole field. But a lot of people were, according to what he was writing, I've been reading his books, and they're great, but they were like dead set, oh, this is the structure, this is how it looks. Then when we actually got the data, well, no, it's actually quite a bit different. It's a lot more complex, and this is how it is. So a lot of theories had that first mindset, and his thoughts were, well, I think that what we see with our Earth, the magnetosphere, and what we see in the interplanetary environment should be taken, because those are the best observations that we have. And then also our experiments with plasma in the lab, that should be the basis for our theories for areas that we can't access directly in situ, which would be interstellar and cosmic. With the cosmic environment, the interstellar environment, you can get, visual images, or you can get images of light. So all the different frequencies, gamma, X-ray, whatever, right, going down to radio. You can use that to guide your kind of assessment, because we see, like, for example, structure to galaxies. We see structure to galactic clusters. They form these filaments and such. So it's like, where do we see filaments in our Earth environment? Do we see filamentary structures within the plasmasphere? Yeah, we see the aurora. They form these ribbons and filaments of plasma. If we see that in the Earth environment, we're also seeing these filamentary structures at the cosmic environment. There's probably some base physics that works across all the different scales that's fractal in nature. And so that was really his mindset, was work off of the plasma experiments and the observational data we have in the lab, also what we're observing in space, and then build out from that. Not just, oh, I had this idea, and let's just create some math that makes it look cool, but isn't based off of any observational data. And as more data has come in, a lot of these ideas that were taken as gospel have, reached the chopping block, but not all of them. A lot of them are still there in use. And, not all, it's not like every single idea we have is wrong. But certainly there's a lot of inertia to ideas, and not, not all these theories are what the reality is. We're always going to be coming up with new and better understandings of things. But I just think his mindset of thinking was really right on it, because it was just very logical. It wasn't fanciful. And I think more people should read his work. I mean, he's well known, but there's this phenomenon that occurs where you have like a scientist, and they come up with all these ideas, but then they're kind of only known for one thing. And so he's known for waves traveling through plasma. They're called Alfvén waves, and there's a whole bunch of different types. So he's really well known for that, but he's not really well known for some of his other ideas for the cosmos, like, for example, matter, antimatter symmetry. One of the big things in astrophysics is, why is there this matter antimatter imbalance? Why we only see matter but we're not seeing antimatter? That just kind of strikes me strange, that if you have these things generated in equal amounts, and that's what's stipulated with the Big Bang, how could one overcome the other in the first place? And they say there's some some quantum particle physics that explains that, but I don't know. My spidey sense goes off.
What is antimatter?
It's effectively the opposite of matter, but you wouldn't really be able to tell what antimatter is until annihilation occurred. Because when matter and antimatter come into contact, they just immediately create energy. So there's nothing left over other than just pure energy. It's the most energetic thing that we know of. Like a matter antimatter collision is incredibly energetic.
So what was his take on the Big Bang?
Well, he didn't think the Big Bang is what happened. His idea was that there was more of a steady state to the universe. And to keep it really simple, is that you have a matter antimatter balance, and we don't know exactly at what level you start to encounter antimatter. I mean, it gets kind of wild, his ideas. But for example, our sun and our solar system could be matter. We don't know if Sirius is antimatter. Sirius A, Sirius B, or Alpha Centauri and Proxima Centauri. We don't know if those stars are matter or not. They could be antimatter. Because the light, there's not.
We can see them, right?
Yeah, there's not light and anti-light though. So
right.
So they're just generating light. There's no way we can tell until we actually kind of get close enough to sample. But maybe they are matter, and instead you get these interstellar pockets of matter and antimatter. So it's a star cluster that's all antimatter, and another star cluster nearby that's matter. Or maybe it's even at the galactic scale that you have this division. He was even talking about there being antimatter chunks in the sun that generate solar flares, and it gets kind of wild. But at the boundary between matter and antimatter, you're going to have annihilation, which is an extremely energetic process, which generates gamma rays. And as a result of that collision, there's going to be a natural repulsion between the two. And so they're going to spread out. And then a lot of that galactic flux, the cosmic, the gamma rays will get absorbed into other mediums and stuff. So it may be kind of hard to detect. But that could explain some of the cosmic flux that we see in the environment. But his idea was that gravity would bring these different pockets of matter and antimatter together over time. And then annihilation would become a process that outweighs them in force, which then pushes them apart again, which then would diminish the amount of annihilation that's occurring because these boundary layers that exist, because they're now far enough apart. There's a low enough flux of matter hitting antimatter. This cushion that exists is now very low energy, that then gravity starts to bring them back in together. And now you get more annihilation, and you get this rhythmic pulsing to the universe across time.
Oh, interesting.
And so the universe could be, let's say, 50% smaller at one point, I don't know, like 10 billion years ago, let's say.
Yeah.
And then it expands out and eventually contracts and expands. It contracts, expands. And that was his, in general, to keep it really simple, that was his idea as to the universe. And, we're not really going to be able to get good data on that until, we actually get probes well beyond our solar system. Voyager 1 and 2 are still basically right at the edge of our heliosphere. So we haven't gone to Alpha Centauri and, set foot down and be like, oh, what the heck is this? So it's a lot of, I just like his mindset of build off of what we have and then go forward with that. And we'll get a lot more answers as to antimatter as these particle accelerators are able to produce more and more of it. And we can do more testing of it, you could say, but we don't have any direct measurements of it.
Yeah, it's interesting. Did you see that there was a recent post that I found, and there was a paper attached to it where I think it was the James Webb detected some galaxies or something that were like, they were so big, they were like super massive galaxies that they would have to have been like, it like throws off the whole timeline of the consensus of like the Big Bang. Did you see that?
Yeah, they just keep pushing things back. And
yeah,
I just personally, I mean, the big.
See if you can find that paper, Steve. The James Webb supermassive galaxy discovery.
The big thing with the Big Bang is there's this cosmic background microwave radiation.
Exactly. Yes.
And they kind of like, okay, well, this is here, and we have this inflation to the universe. Then let's just wind the clock back, and it comes to a singularity. But if there's other dynamics, like for example, this pulsing that we discussed, you could wind it back, but then maybe it doesn't actually go all the way to a singularity. Like maybe you should stop winding the volume, the clock back at a certain point, because it actually doesn't go beyond that. So there's like a lot of assumptions that have been made. But I don't know. I just explore with an open mind. I'm just a young chap who's interested in this.
Yeah.
I feel like I have a fairly good spidey sense, and I think it's good to ask questions.
Is this it? This is March 2025.
This is the announcement.
Oh, okay. Is this on? This is on the NASA website. Oh, yeah,
NASA,
NASA.gov. So let's see what the summary of the top says. Using a unique infrared sensitivity of NASA's James Webb Space Telescope, researchers can examine ancient galaxies to probe secrets of the early universe. Now, an international team of astronomers has identified bright hydrogen emissions from a galaxy in an unexpectedly early time in universe history. The surprise finding is challenging researchers to explain how this light could have pierced the thick fog of neutral hydrogen and filled space at that time. The James Webb Telescope discovered an incredibly distant galaxy, JADES GSZ. How do they come up with these names? Z13-1, observed to exist just 330 million years after the Big Bang. In images taken by Webb's NIRCam near infrared camera as part of James Webb Space Telescope Advanced Deep Extragalactic Survey, researchers used the galaxy's brightness in different infrared filters to estimate its redshift. Right, its redshift, which matches. See, I had a dude on here recently. I was trying to show this to me, and he was trying to tell me this was like some crock pseudoscience, but this is on NASA's website. So this thing is so old and so big, they have to push the timeline back. Yeah, because of the redshift.
I mean, they do incredible work. And if you look through some of the, like this book that I'm reading right now by Hans Oliven, it was co-published with NASA, but it's from like the 80s. So there was a much more open-minded spirit of investigation back in the 50s, 60s, 70s, 80s. And there have been a variety of people like Freeman Frund, who, looked into rock circuits and the electromagnetic dynamics of earthquakes, and he was with NASA. So, it's not like they're all closed-minded people, but I think when it comes to what's presented to the public, there's this filtering that's done, and I guess that makes sense, but it's kind of just, we're going to show the things that we're the most certain about, I guess, but some of the things that are presented that they're the most certain about, I'm like, I'm just not so sure about that. Just because a lot of people in the room are saying the same thing doesn't mean they're all right.
Right.
I've seen that play out so many times in history. So
yeah.
There's a lot of really cool things though that come out of NASA, that come out of NOAA, a lot of amazing people that work there, USGS. So like, it's just that these organizations kind of grab a lot of these people, and I see things becoming more decentralized in the 21st century. So I think we'll see more people chart their own course and do their own independent research. And
yeah, but it can lead. The problem with that too is it can lead in the opposite direction, where it's like nothing that the science and like the academic science or these whatever you want to call them, so-called gatekeepers say is true. Like everything they say is a lie, and everything's a cover up, and everything's a conspiracy, and everything is not what it seems. And it's like it just becomes this crazy cult type mentality that people have.
Yeah,
especially online.
Tell me about it, bro. That's why psychology, I mean, I'm not a psychologist, but you have to learn a little bit about it because you just see it play out in front of you. And if you want to not be, I don't know, if you don't want to be a sheep, you got to kind of spend a little bit of time in all these different things and to learn about them. because it's important. And you see,
well, it's crazy. I mean, just to use a recent example of that 3i atlas, it was like, you saw like incredible division online of what this thing could have been. You had either it was a space alien spaceship coming from some other star system, or it's just a comet, right? Like there's no in between there. It's become this game of questioning people's motives instead of actually interpreting the data and attacking the substance of what is happening. And when you're just reading stuff online or like watching YouTube videos and you don't really have the time to like look at this stuff and like look at the raw data and come to some sort of conclusion, it's like, all you can do is just rely on other people's interpretations of stuff. And oftentimes you're going to get that wrong.
Yeah. How much have you been tracking the 3i Atlas story? Because I've been doing a ton of research there.
I haven't really. I heard that. So Avi was telling us that it was like December 16th was when it was going to be closest to Earth, right? And that was the time that we were going to have like the best shot at it to figure out what it was. And I haven't heard anything about it since. Have you been tracking it?
Yeah, I mean, it popped into view, June 1st or July 1st. We first caught our glimpse of 3i Atlas, and then I jumped on that pretty quick because it was interesting. But yeah, it became this bifurcated, kind of oppositional warfare between there's 4 million draconian soldiers on this thing versus it's just a comet. Meanwhile, our definition of a comet is built off of just I don't know, like 50, 100 years of observations.
Sure.
And some historic eyewitness viewing, but space is so much more vast and dynamic than we know. So to call everything just a comet is a little short-sighted. Because comets have a fairly low bulk density. It's mostly ice and these volatile gases that are turned into ice, like CO2 ice and methane ice. And, they start to vaporize effectively as they get close to the sun. But one of the key things is that they're kind of fluffy and they have a low density to them. 3i Atlas has shown some signatures that it's not just that. It's had these tightly collimated jets. So that sunward facing tail is one of those. It extends out quite a bit, and it's not just like a shotgun super diffuse. It's fairly tightly collimated. And we've also seen jets come off other locations of it. And I mean, we've seen this like jets before with comets and such, but 3i Atlas certainly is different. And one of the things that we see in space is that you often get jets when there is a central body that's rotating, that's magnetized. That seems to be a key factor in the production of jets. So if you have a rotating central body and it's magnetic, has an endogenous magnetic field, that can create the structure to collimate these flows of plasma. So we see that certain galaxies, you have the centrally rotating core of the galaxy. It's highly magnetic because it's made up of all these stars and whatever, maybe black holes. You have these jets coming off of that. Supernovas, same thing. So there's some evidence that this is kind of what I think, based on my research, that 3i Atlas may have a level of magnetization to it. And there's even some processes that can occur in interstellar space due to the processing of cosmic rays that would generate magnetite in situ, which is magnetic. And so if 3i Atlas does have a strong magnetic field and it is rotating, we know it's rotating, but how fast is still kind of open. They say it's like 16 hours. I think it actually may be rotating faster than that, but there's no hard data on that. But there's really not that much data on this thing in general.
Right. We haven't been observing these interstellar objects for very long. Like this is the third one, right?
Yeah. And since it came in super fast, like how did it get that speed, right? Its trajectory through the solar system, while very unusual in terms of it being aligned with the ecliptic plane, passing close to Mars, and then passing close to Jupiter in March, that is just kind of a random thing. Unless it is, intelligent by nature, like it was planned. But there's always weird trajectories that you can draw up. So the speed, though, is key. It's traveling super fast. What gave it that velocity, or at least relative velocity to us?
Well, if it was interstellar, right, how would we know? We don't know how fast interstellar objects typically go, do we? I mean, we have 3 to measure. So
exactly.
If it's coming from some other star system, it would have more time to gain momentum, maybe?
Or how is ejected. Yeah. So there's a lot of different ideas, but I mean, one idea is that you could have maybe a planet just get through tidal forces just totally fractured apart. It passes too close to a very, like, let's say like a red dwarf that just rips the planet asunder. And if it's Earth, Earth has a significant inner core. It's made up of iron and also nickel, and it's magnetic, like all this stuff. You could have a chunk of that perhaps fly off. And if that's going at fast enough speed and it has magnetization already, you don't just lose that.
Right.
There has to be a process for that to get lost. Then that could, if this thing is compositionally different, and that would also have a much higher bulk density, like the bulk density of that would be like 8 grams per centimeter cubed, whereas water is 1. A comet bulk density is roughly about 1 gram per centimeter cubed. It could be dramatically different. We haven't landed a probe on it. We've landed probes on comets before. We've done some missions like the Rosetta mission, but we didn't do that with 3i Atlas because it kind of came out of the blue too quick, but
Going super fast.
So there's a lot of unknowns, but yeah, just to throw a label of comet on it, I think is premature. So we call it a interstellar object.
Right.
But then also to take the word of, I think these people are amazing in the spiritual community, like channelers and psychics and all that. I think there's a lot of cool stuff there. But just to take the word of a channeler who's like, there's 4 million draconians there, and that's 100% your perspective going forward. I'm like, I don't know. That's also the exact same as this person saying it's just a comet, just on the other side. And so I made a lot of videos about exploring all the different perspectives, and guaranteed every video I made, some people were, thrashing me online for saying, I can't believe you think it's a comet. Meanwhile, I'm calling it an interstellar object. And other people saying, I can't believe you're not, recognizing that's 100% alien filled with draconian soldiers. I'm like, guys, I'm just presenting all the different ideas in the middle, interstellar object, but people see what they want to see.
So, was NASA able to get like a super detailed image of it on December 16th when it came as close to the Earth as it was going to get? Are you aware of that? And then what were we able to analyze from that?
So there were weird things that happened. I mean, we had this government shutdown in October.
And they weren't releasing the images that was like the Mars orbiter or whatever.
Yeah, and see, Loeb, he really pumped up this Mars Reconnaissance Orbiter imagery. Like if you, and he's also edited a lot of his blog posts.
Who? Avi? Has he?
Yeah, so because there are certain things that he said, which, I mean, rightfully he edited them because they turned out to not be, I think he got a little carried away at times. One of them was with the Mars rover. It has a mass cam that looks at basically the sky every single night in general. And there were some weird things that we were seeing. And one of the images is Phobos, but the internet community took it and said, that's 3i Atlas. And he posted.
It was a moon?
Yeah. And so he posted that. And then he went back and edited the article later, which is fine. It's good to be, accurate rather than leave.
But does he leave like a footnote saying that he made an edit? I
don't know about that. But going from basically probably August through September, he was talking big about the Mars Reconnaissance Orbiter, the HiRISE camera. We'll get our highest resolution look. We'll be able to, focus in on that nucleus, see exactly what it looks like. And then when it actually got the imagery, he's like, I'm not surprised it doesn't look that great. But, there's this thing with public communication, whereas if you're communicating, you have to expect that people are going to sometimes take that information. Maybe they don't hear your future updates. You have to be very clear and nuanced with your communication, I feel like. And the imagery we got from NASA was the highest resolution imagery we got. But there was a lot of improper communication with it because these amateur astronomers, which were doing amazing work, getting imagery of 3i Atlas, they're looking at the whole thing. The tail, the coma, you're not seeing the nucleus because the coma is so thick, this envelope of gas, dust, plasma, everything. They're seeing the whole thing. NASA was zoomed in on the coma. And so that's why it looked like a blurry blob. Right. Because you're not seeing the tail or anything. You're punched in on the coma.
Yeah.
But they did kind of a poor job at telling people about this because, they were very adamant that it's just a comet, and they had this whole press conference, and, They did some weird things too, which I kind of questioning why they behaved a certain way.
Who, NASA?
Yeah, there's some oddities across the board. But in general, they did give us our highest resolution, but people also, they want certain things. So they wanted this to be, some starship. And when the imagery came out that it wasn't.
Was that the image, Steve?
Yeah. So I got two sets of images for you. So this one right here is the Hawaii telescope, Subaru telescope in Hawaii that took this on December 13th.
Yep.
And it's just this fuzzy ball.
Okay.
That's great. And then here's a more cooler one.
Whoa.
From, I'm guessing, one of the space stations.
Oh, this is a G3 Atlas, though.
Oh, this is
it's a different one.
G3?
It's 2024, October 1st.
That's so cool, though.
Oh, it says 2025 here. Okay, well, then never mind.
But that's what a typical comet looks like.
Right.
This one's super cool.
Wow. But yeah, so that one's got a typical tail of a comet, right?
That's R2 Swan.
But then
It's a lemon.
this is 3i Atlas.
There's no tail on this one, really.
Now, that one's probably pretty punched in. We're seeing it's only 10 arc seconds across. So that's a pretty high resolution look at the coma. And the thing is that these telescopes, that's what they do. They don't take good wide view pictures of space. If they want to get that, they have to take multiple pictures and then create a mosaic and stitch them all together.
Right.
And if they're only focused on understanding the coma and the nucleus, we don't need to see the tail. But NASA probably should have taken some time to get those wide angle views because that's what everyone wanted. And they're accusing them of all this crazy stuff. And there are some weird things happening. So it's not helping them by them not doing the work, you could say. But to answer your question, Hubble started taking a lot of imagery of 3i Atlas up to this moment in time. So starting November, December, and up now, they've been taking a lot of imagery of it. But still in the raw state, hasn't been processed except by a few amateur astronomers. They're processing the Hubble data, which is showing these jets go off, which is some of that observational evidence that maybe 3i Atlas is magnetized. And the Rosetta mission by ESA, the European Space Agency, when they flew a probe around this comet that they were tracking, they actually picked up a magnetic field around it that typically had a strength of 30 to 50 nanotesla. But when a solar storm hit it, it went up to 300 nanotesla. So a comet, a traditional, regular comet, can already have a pretty significant induced magnetic field. So you can imagine if the object itself, let's say 3i Atlas, has remnant magnetization to it, and it is spinning fairly rapidly, then you could create the conditions for these sort of astrophysical jets. And what we see across the scales is that there is a fractal nature to reality in the universe. And so if we're seeing astrophysical jets at the galactic scale and at the interstellar scale and at sometimes the actual a single star exploding at the supernova scale, why can't we have jets with maybe a smaller object? So there's a lot of interesting things there.
Yeah, it's wild.
It's a big mystery. I don't know what it is. I think it's a unique.
It's exiting our solar system now, right? It's on its way out.
Yeah. It's leaving now, and it would have to do something dramatic for that to change because it's moving so quickly. About 65, 66 kilometers per second right now, roughly. It's sped up with its closest approach to the sun, its perihelion, to 68. Because gravity, is actually accelerating as it gets closer to the sun. And then that deviates its course a little bit.
Right. It's got an arc.
The fact that it only deviated a little bit shows you just how fast it's going.
Yeah.
Because most comets, they'll have a huge deviation in their orbit. But 3i Atlas was just it wasn't even 45 degrees. It was probably 15, 20 degrees.
Yeah, we had this gentleman on the other day who was explaining to us there's this NASA mission where they sent a probe to land on an asteroid. And I can't remember the name of the asteroid now.
Bennu.
But Bennu, that's what it was. Oh, you're familiar with this one. And I think the goal was to they were looking for life on the asteroid or something like that, or consciousness or something like this.
They found a ton of organics, amino acids. They found these gums, which are, from what I know, weird assemblages of amino acids. So not exactly
OSIRIS-REx was the name of the mission.
Yeah, not exactly proteins like we know them, but they found more of the ingredients for life than they expected. And this is a B-type asteroid, which compared to other types of asteroids, specifically like D-type asteroids, are less enhanced in these organics. And the asteroid belt is made up of like there's multiple distinct populations within the asteroid belt in terms of composition, but also in terms of where they're from. So there's objects that have come in from outside the orbit of Neptune in the Kuiper belt. So trans-Neptunian objects have come into the asteroid belt and found a home there. And it seems that there's higher concentrations of organics and amino acids and things like this when you go further away from the sun, because sunlight kind of processes this these compounds and degrades them, it seems. But the interstellar environment seems to be more conducive to creating or preserving them, and or both. So we have objects in our asteroid belt that have come in from the Kuiper belt and found home there. This is a B-type asteroid, which is like a standard normal asteroid. If they landed on a D-type asteroid, or if they send a probe out to maybe one of these objects floating well beyond Neptune, who knows what they might find. It's really quite exciting stuff, and full of open possibility. But we haven't found, as far as I know, like complex proteins yet. They found these, what they called gums, which are, I guess they would be proteins because they're like amino acid assemblages, but I guess they're different than standard proteins that we know. Maybe the folding is different.
Right.
So, but yeah, cool. Really cool stuff. So, I mean, there's a lot of great stuff that's being done. And that's why I think it's kind of toxic when you just look at everything and say, oh, it's all nonsense. Space is fake, right? It's all a conspiracy.
Yeah.
That doesn't help anybody.
How serious do academics take the whole younger dryas hypothesis? Do they just brush that off as pseudoscience, or do, in your experience, like real academic geologists and people like this take that hypothesis seriously?
I can't really answer that question because I wasn't even aware of that when I went to school. We never talked about it.
Right.
It wasn't a topic of discussion. Maybe if I'd, taken a master's or PhD, it would have, but then you start to specialize. And so, I think a lot of these, I think in general, unless you have a innate interest in it and research into whatever the topic is yourself, a lot of people just kind of go with whatever the idea is that's floating around. And so if a lot of your community members or academia and, professor friends or whoever, all just kind of repeating the same thing, then you probably just go with that. And it kind of takes some initiative to research into something yourself in depth and come to a more nuanced view.
In these academic fields, it just seems to be like there's not as much curiosity into this kind of stuff. But like the reason I'm asking that is because in that black matte layer that they found in the strata of the Earth, there was like little nano diamonds and certain metals that you would find in comets and asteroids, right?
Yeah, the micro evidence.
Yeah.
So I recently had Randall on my show, and we just talked about all this stuff, and I was actually on his as well. But yeah, Randall Carlson's looked at the macro evidence, geologic structures, and he relayed this spiritual experience he had when he was a teenager of seeing the actual water flowing down these massive gorges. And he said it's like a visceral spiritual experience that guided him to then investigate what he does now, 10 years after it happened.
Right.
And I think there's a lot to that. I don't think that should be just immediately dismissed as like some mind fantasy. Sometimes the best ideas.
I mean, that's a huge question. Those scablands, those channeled scablands in the Midwest, his theory on it is that there was like a billion quadrillion tons of water flowing through that or something, because there was the Laurentide ice sheet that was above that, that somehow like melted instantaneously on upon impact of some sort of comet or a bunch of comets, melted it, and then this quadrillions of tons of water started flowing through and carving out those channeled scablands. And if you look at it and you zoom out and you think about that, it does look like that, right?
Here's like a close-up version.
Yeah, and if you really zoom out, like a lot of the land in that part of the country, and even if you want to go into like Southern California area, it looks like it's the bottom of the ocean, like an ocean floor, you know? So
there's something to it.
There's definitely something to it.
The universe is fractal, so sometimes you're going to see at bigger scales, and the larger a process is, sometimes the harder it is for us to like grasp it with just kind of like visualizing it or more. And I mean, evolution used to be thought of as just like, you know, a slow, steady, homogeneous process, but we know that there's periods of punctuated equilibrium where there's rapid evolution that occurs because there's some force that causes rapid evolution. And then there may be, you know, more steady grind of evolution for 50,000 years, and then in 500 years it's really rapid because maybe some disease outbreaks or there's some new pressure placed on the island or whatever it is. And I think the same is for geology. And so the thing with these, you know, channeled scablands and Randall's idea and other people too is what deliver the energy to melt the Laurentide ice sheet so quickly.
Right.
The traditional idea is that you had, I think it's Lake Algiers. I could be, I think that's right. That's sitting at the base of the Laurentide ice sheet. There was an ice dam, and then that broke down.
Exactly.
And that flooded out. But based off of Randall's geologic trips all throughout that area over decades, right? He's like, that's not big enough. That's not significant enough. Right. And it did go away quickly. And we have the climate data to show that, you know, the Younger Dryas was a massive, you know, basically pulse of volatility for 1,000 years or so. And
he also talks about this isostatic rebound effect that would have happened. Like if the ice sheets would have melted because there's weight that they put on each end of the earth, right? And that somehow keeps us in some sort of rotation or keeps us balanced somehow. And if all that ice melts, all of a sudden the Earth's crust will expand and create this isostatic rebound. Yeah, and are you familiar with that? That's been measured in Canada and the location, and even like down to the Great Lakes and such. So where the Laurentide ice sheet was, there is this active uplift, though it's, you know, certainly slowing down now as compared to when it first, you know, the ice sheet first melted. But his interesting idea, which recently got put on my radar when I was talking to him, is that if you have one location, you know, now having this rebound, there's likely going to be another location that's having this depression. So he thinks the Azores is that location. That's why he thinks that perhaps Atlantis was there. Because if you look at the bathymetry data for the Azores, it's actually quite deep. And so if you were to drop sea level 400 feet, which is where it was during the last ice age, it doesn't really create like a plateau. But you had the Laurentide ice sheet over North America, and then you also had a very like large ice sheet over Europe, specifically like Scandinavia. Right. And that's 2 points of the plate junctions for the Azores, because you have the North American plate, you have the European plate, then you also have the, I believe it's the African plate meeting there. You can maybe pull up the plate tectonics of the Azores, but either way, you have this plate junction, triple plate junction there. And if two sides of that are experiencing this rebound, right, off to the edges, then at that junction perhaps is where you're having this subsidence occur. And that would then explain it, because if the isostatic rebound for North America, where the ice sheet was, is, you know, 1,000 meters, 2,000 meters, because it was that depressed, then that would have somehow made the Azores sink? Yeah, maybe now because there's this equalization that's occurring, they're now sinking. Think of like if you have a plate and you have the ice sheet weighing down on the corner, that these plates seem to be more structurally, the African plate. So these plates seem to be more structurally intact and rigid than kind of maybe we currently think. Right. And so at the edge, that would perhaps lift up, raising the Azores into a bit of a plateau. And then when those ice sheets go away, now they would sink back down. And what we have is what's been left. Right.
This is just an idea, but I do think it's worth considering. It's captured my interest because we know that, rebound and subsidence exist.
Right.
And it can happen quickly. In the Central Valley in California, they're pumping the aquifers like crazy for all the almonds and farmland there. And there's places where it's dropping like a foot a year, like 2 feet per year, like rapid subsidence because they're draining the water tables.
Wow.
And that's just from like pumping water out from aquifers. I mean, imagine kilometers high, like Game of Thrones style ice sheets, even bigger, right? It's totally different dynamics that we just don't have a concept of in the modern day.
Yeah. Didn't Randall go and like go to the Azores and like explore it?
I don't know how many trips he's done there, but when I talked to him just recently, I mean, he was just there like, I think November 25. So just recently he did a trip there to look for geologic evidence of some of his ideas. And I haven't been there myself, but I think there's a little bit of truth in all these ideas that are floating around, and there's a lot of conspiracies attached to them, which can be fun. But I'm more interested in finding those truth gems, you could say, and seeing how they fit together and getting a better sense of the past. Because if you truly want to understand the future, then we need to see what's occurred in the past and kind of maybe see the direction that's leading us. And you're not going to do that if you're affiliated with one side or the other. It's just the sun causing the climate. It's just CO2. You're never going to get to the truth that way. You're just going to fool yourself. So
yeah, you have to be interdisciplinary, kind of have a hand in a little, touch a little bit of all of it, right? To have a real like broad picture of what's going on.
Yeah. And we're tribal at the end of the day. So I think a lot of people, they really need like community, society. They need a tribe.
Yeah.
And maybe I'm a bit of a outsider in the fact that, I'm pretty chilling. Great. If I have friends, cool. If I don't have that many friends, whatever. Like I'm more focused on seeing these bigger patterns, and I don't need to fit in.
Right.
Really. I think there's a lot of things where you fit in. It's not to your benefit, actually. Anyone that gets, anyone that's contrarian, for example, in the stock market, let's say it's going up, and it's about to have a crash. No one knows that yet. Michael Burry, he puts in the Big Short, worked out very well for him. So
not so much sense though.
Yeah, now everything's a Big Short for him.
Right.
But these just kind of ideas, like I think a lot of it's programming, just learning to kind of separate yourself from that. And this requires a lot of internal reflection to see what your processes are.
Yeah.
And that's an inner journey that we're all taking, and some people maybe do it faster than others, and different paths of exploration. But
yeah,
I think a lot of the problems in the world would be solved if more people looked internally. And
yeah, totally. Well, you spend a lot of time on YouTube, and you're exposed to a lot of these crazy rabbit holes. Did you pay any attention to that recent scan beneath the pyramids? Where those Italian dudes said they found these big cylindrical shafts that go kilometers under the earth.
This is interesting because we're starting to see the hive mind coalesce around the idea and make it more solid. And it's really interesting. I was at Cosmic Summit last year where they were and they presented. Unfortunately, I didn't get to see their presentation, but I've read some of the research on that sort of data collection. They're using satellite pairs in space, and they're doing radar measurements, and with super high precision, they're measuring the differences. But there's a lot of factors that go into it, like the polarization of the wave, the timing of it, even the atmospheric factors like distortion of the radio waves. All this influences that data. And so I'm just in kind of default, skeptical is not the right word, but cautious as to any interpretations that are made, because they presented some pretty astounding, compelling results that are very detailed.
Yeah.
In this data collection method, from what I know, because being in all the geophysics stuff, I'm able to read that paper and for the most part understand it. And I was still reading, I'm like, this is pretty out there. So for the average person, they're not going to be able to read that research paper. So they just got to
They
take
just look
it
at the AI remake and be like, holy shit.
There's
Elevators under the pyramid.
They got to take it by faith. So
Yeah.
I don't know what the deal is there. The geology probably is conducive because it's a lot of like sandstone, limestone and stuff.
Exactly.
It probably is conducive for that, for having these structures. But I mean, they're talking about massive, massive structures.
Have you seen the raw data?
I mean, they have
The raw scan data?
Yeah, it's quite a bit different than the 3D
Quite a bit.
abstractions that they
Quite a bit
showed.
different, even from not even talking about the AI renders that other people have done.
Yeah.
But quite a bit different from those Italian dudes, their render of it.
Yeah.
Like they scanned the Khafre pyramid, the central pyramid, and they show like 7 king's chamber size chambers in the center of it. And we know for a fact that they're not there. So like why are they showing 7 different king's chambers inside that central pyramid when that whole thing's been explored and we know for a fact that those aren't there, you know?
It's interesting. It's from space. It provides like a broad view. If it was to stimulate a rigorous and robust, let's say, seismic and resistivity survey of the Giza Plateau, then that'd be amazing. Like if that's the end result of all this, that'd be great because we could get high resolution data for the Giza Plateau in a way that provides maybe not irrefutable, but pretty conclusive proof of voids and structures underground if we use that combination. Again, 2 methods, seismic, which has a huge track record of success for exactly these sort of investigations.
Right.
And then even better in some aspects, resistivity, where you're measuring the electric current flowing between different electrode pairs, and then you track that across depth and time and all these different frequencies, and you get that data, and that shows void structures or tunnels or things of that nature very well.
Yeah.
You did a widespread 3D seismic and resistivity survey of the Giza Plateau. You could pretty definitively be like, yes, there's something there, or no. Much more so than this radar data from space,
Right?
The SAR data.
Yeah, there was a lot of squirrely stuff that was happening with that SAR data, and even like their first analysis, like their descriptions of it, and like their descriptions of their scan of the Khafre pyramid and why they couldn't detect the shafts that go underneath that central pyramid. In their first paper, they described that reason being they can't go that deep into the bedrock, right?
So you read a lot of these papers yourself.
Oh, we recently had like this guy on here, Jeffrey Drum, who he lives in Giza, like right by the pyramids, and he's been there like on the ground studying this stuff for years now. And he has a great YouTube channel called Land of Chem. And like he's been hyper focused on this stuff, reading papers. Those Italian guys invited him to their first little presentation that they did in the beginning of 2025. And he was there asking questions, and like one of his biggest questions was like, how come in your first paper when you scanned the Khafre pyramid, you explained that the reason you couldn't find the shaft under the Khafre pyramid was because you can't see that deep into the bedrock. Now you're doing this and you're saying you have kilometer deep shafts underneath the bedrock, like, and you know, to the Italian guys' credit, they weren't coming up with some crazy excuse. They were just saying, we don't know. Well, I don't know. They were saying they don't know. So there's definitely a lot of very strange questions there about that. And like, again, like Jeffrey, we came here and he was showing us the raw data, like the raw scans of what they were able to do. If you can find those, Steve, of those shafts. And it's just, to me, it doesn't make sense how they were able to jump from that raw data to their 3D render. Maybe there's something there I don't understand. I'm sure there is a lot I don't understand about this. Yeah.
Looks just like it.
Well, this is yeah. So that is supposed to be on the right, a side view of the Great Pyramid, I believe. Find that, and then that's, you know, the one on the right there, that vertical one, Steve. That's supposed to be the shafts under the pyramid. And if you look at that next to there, yeah, go to that one in the middle, Steve, where it should, yeah, that one right there.
The other thing to be mindful of, because this data is very similar to GPR data. It's actually effectively GPR just at a much larger scale, lower frequency, you know, from space, but it's still electromagnetic waves. What's the polarization? What's the frequency of this stuff? With GPR, there's like a million ways to process it, depending on what filter you put on it.
Right.
You know, ideally you kind of learn how to process the data and you do it as objectively as possible, but it's not that difficult to all of a sudden make one quote unquote anomaly pop out versus another based off of like what your cutoff is for the colors. Like even just the color scheme, what colors show up for what values, just even changing that can all of a sudden make that look radically different. But the end result, the person who sees that just in a 5-second scroll on social media, right? They're just interpreting the colors that they're seeing. They're not obviously seeing, 5 different color renderings. And that's like the most basic of things. We could go through all the different filtering options that exist, low frequency cutoffs, high frequency, all this stuff. So
so these guys published a paper for peer review, I believe, and they're waiting to see if it's going to get published.
Okay.
But I'm not sure if it's going to be, and their hope is to be able to get permission from Egypt to do more excavation and figure out what's going on there. But Jeffrey, who lives in Giza, he's saying that he knows people in the antiquities department of Egypt, and they're all super angry that these guys did this without like consulting them. So he's saying that those guys are never going to get permission to move a grain of sand on Giza because of that. Because they did this sort of like cowboy style, even though it's from like satellites, right? Like technically they're not like violating any laws or anything. I guess the fact that they did it the way they did without even talking to the Egyptians, they got their panties in a bundle. But it's interesting either way.
Have you been to the pyramids?
Never.
Oh, it's crazy.
I want to go. You been?
Yeah, back in 23, it's funny because I was watching Ancient Aliens.
Oh yeah,
and it was just like something I put on while eating like I don't know lunch or something. But they visited the Temple of Isis in the Aswan area for that show, and it was only like a 30-second clip, but I was like, oh my god, like I need to go there. So like a month later, I'm there.
Wow.
Because I was free reign, like basically Lone Ranger. I could do whatever I want. So I flew there, and it was only a 10-day trip in Egypt, but Luxor, Aswan, going to Giza, and also I saw like, I don't know, I went to 5 pyramids. This guy you're talking about, he lives there. But even just in that trip, like you can feel the energies. Like there's all the symbology. It's, a lot of the shapes and structures and like sacred geometry, it influences the energetics of the environment. And so Egypt seems to be just loaded with that.
Yeah.
And then all the intention put into these temples and sites over not only hundreds but thousands of years seems to leave like a long lasting, powerful, energetic imprint. And then there's people that have reported certain shrines will create like weird symptoms, like or electromagnetic interference with like cameras and stuff.
Really?
I don't remember which stone it is. There's like one temple that has this special stone that causes weird reactions with technology, and even some people will feel really weird around it.
Really? I
think it's like a rock carving of the lion goddess. Is that Sekhmet maybe? I can't recall exactly, but there's people that have talked about that. So there's like weird things there for sure. And if we find out that there were, maybe structures under the pyramids, I wouldn't necessarily be surprised.
One of the things that Jeffrey is saying is he thinks he doesn't know for a fact, but he has discovered iron veins around the edge of the pyramids. And he thinks it's very possible that there's natural iron vein deposits underneath those pyramids. He has an elaborate theory on how the pyramids were basically chemical processing plants. And his theory incorporates all of the pyramids, not just the Great Pyramid, and how they would have used like ammonia and sulfur production by basically using like the natural resources of the earth to create these chemicals, which could have been applied for things like agriculture or even metallurgy. So he has like it's kind of like an out there hypothesis, but it makes rational sense. It's not aliens and it's not tombs. It's kind of like a little bit of an in-between that makes a lot of sense. And he spent a lot of time in those pyramids. He even showed a guy who made a 1/20 scale model of the Red Pyramid. And it was it ammonia they were processing in the Red Pyramid?
I don't remember.
I believe it was
supposed to
ammonia.
be high pressure.
It was like a high pressure chemical processing, and they replicated it with all the chambers of the Red Pyramid in like a small model, and they were able to replicate it. And but the model exploded because his theory is that like all of the blocks that are stacked on top of it were. And in that perfect symmetry of that pyramid is supposed to be able to contain that pressure, and that high pressure creates those chemicals. It's wild. It's deep. It takes a lot of time for him to explain it and to understand it, but it makes so much sense, man.
Yeah, I'm aware of some of his work because I started watching part 1 of his interview with Matt Bell, who did like a 9-hour podcast with him.
Yeah.
And I'm like, I'll get through this, but I haven't finished part 1 yet.
Yeah.
There's part 2, there's part 3, but he started laying out a lot of groundwork as to ancient sites and their use, and like high points form these positive charges because they naturally accumulate there, and lightning strikes.
Exactly. The Telluric currents and the lightning strikes have like a lot to do with it, and he connects that to different sites around the world.
It's very interesting.
Yeah. If we were to go to another planet and colonize another planet, the first thing we would do is build factories there so we can manufacture our own stuff. We wouldn't bring all of our own stuff. We would figure out how to utilize the resources of that planet or that moon or whatever it was to be able to manufacture. Like utilize the resources that are already native to that location and figure out how to build and create all the new stuff there. And if there was some sort of civilization that was coming here to colonize Earth, well, that's exactly what those pyramids were. They were using the natural resources of the Earth to do things like agriculture and metallurgy and that kind of stuff. And he incorporates it in everything. There's crazy theories out there to like, was this some sort of like Tesla machine, right? A free energy machine, right? And then it doesn't incorporate all the pyramids, it just incorporates the Great Pyramid. What's interesting about his theory is that it doesn't just incorporate all of the pyramids in Egypt. He also can tie it into all the pyramids in South America and Central America and Mexico. And he connects the dots between all of it. And it's just so compelling, man. It's hard to ignore.
If we really want to figure out what was happening and why these are created, you have to think about, there has to be some payoff for that. I mean, you're not going to create these things for no reason. There's got to be some reason, and it's got to kind of be universal across time and something that would be fairly easy to figure out.
Yeah.
Or you have you just see it clearly, observationally, like some of the first, let's say, rocks that were thrown in a fire, all of a sudden you get copper out of them. You're like, oh, that happens frequently enough around the globe that all of a sudden copper smelting kind of popped up everywhere. Roughly the same time. Some places earlier than that because, for example, Michigan, they have like float copper that's just on the surface. So they had those tools earlier, but you kind of need it to be something like that, where anyone can kind of figure it out. And I would need to look more into his stuff, but certainly anything that is related to agriculture is probably going to be closer to it than something that's totally fanciful.
Right.
And yeah, there's just a lot of unusual things of like technology being replicated around the world at the same time.
Yeah.
Which is kind of bizarre. I don't think you need, though, like some explorers of a lost civilization transmuting those ideas outwards necessarily to explain that. I don't know how familiar you are with the Schumann resonances, maybe a little bit.
Not super.
Yeah, they're these resonant energy fields that exist on Earth that are generated through lightning strikes primarily. There's like 50 every second or so around the world. And they produce energy across the entire light spectrum, sometimes even gamma rays. So like a super bolt, it'll be so strong it can produce gamma radiation. But of course, we see the visible light when we see a lightning strike. So it's producing visible light. If you get close enough to one, you could feel the heat from it. That's infrared, the thermal. It produces ultraviolet, extreme ultraviolet, X-ray, but those quickly get absorbed into the atmosphere because they're very high frequency. But it also produces radio microwave frequencies. So you can pick that up, and when there's a big thunderstorm overhead, that can kind of scramble the lower frequencies in the radio microwave band. But the frequencies going from 0 to 50 hertz are such a low frequency that they don't get absorbed easily into the atmosphere or even into the ocean or the surface. So they form these standing waves. And specifically, 7.8 hertz is approximately the frequency and therefore the wavelength of the circumference of the Earth. Because the Earth's circumference is 40,000 kilometers. And you take the speed of light, which is 300,000 kilometers per second, you get 7.5 hertz as the frequency. And what we see is that at about 7.8 hertz, ranges from 7.2 to 8.5, 8.6 or so. But at that frequency, we see an elevation in power as compared to all the nearby frequencies, let's say like 6 hertz or 10 hertz. Those aren't elevated in power, but 7.8 hertz is, and it's consistently elevated in power. Then 14 hertz is a second mode, so a higher frequency. It's also harmonic with the Earth. Not as much power as the first mode, the foundational, but still elevated over normal. Then mode 3, 4, 5. That's the same architecture frequency as our brainwaves, which I touched on at the very beginning, and they have the same strength. So Schumann resonances are measured in the picotesla range, which is very, very, very minute. It's a 1,000th of a nanotesla. And Earth's magnetic field is like, 23,000 to 67,000 nanotesla. So these are extremely minor variations. But when we measure brain waves, they also come in at the exact same range in picoteslas. So if you have the same strength and frequency, that means there can be resonance between them. Because if one was stronger than the other, though the same frequency, then one would be considered noise and the other would be considered signal. So if the Schumann resonances were 10 times weaker than brain waves, maybe there's a mechanism to extract information from that, but the signal of our brain waves would be 10 times stronger. So it'd be difficult to get any data out of that. But if they're exactly the same strength and frequency, then the brain could theoretically grab information from the Schumann resonances because energy is information. There's always information encoded into any energy waveform. So if we have this natural resonance with the Earth that we evolved with, it's probably going back to our evolution. It's kind of a pretty deep thing, but that could then perhaps be an explanation for this dissemination of ideas that pop up all at the same time. Because if one person figures something out, and they're thinking about this, and maybe that just permeates into the Schumann resonances, and then it's the speed of light. So 8 times per second, this thing's pulsing for the foundational mode. Then someone in South America, the other person's in Asia, it could happen maybe the same day. All of a sudden, like they just get hit with an idea. Everyone's had that experience. Where they just get hit with an idea and it doesn't feel like yours.
Right.
It just feels like external, like, whoa, okay.
Yeah.
Especially if you do any sort of like psychedelic, then you really explore into these fields and you realize that, consciousness is a lot more open and expanded than we think it is.
Is this like a different approach to morphic resonance, like Rupert Sheldrake's idea? Is this like was he talking about the
Yeah, it's all this would be the actual, like you could say, electromagnetic layer that could explain that. Morphic resonance would exist across like basically everything.
The universe.
Yeah, I mean, at a consciousness level, at an electromagnetic level, a whole bunch of things. But this would be a specific subset that could help explain this.
Right.
But they've done experiments tracking the Schumann resonances in the Earth environment, and then also someone's brainwaves at the same time. And they found time periods where they entered into coherence with each other, because they can look at the frequency, the phase, and see, okay, we have coherence for 1 second or 5 seconds. And the research in general is that what they call an atom of thought, which is like the base smallest unit of like a thought. It's it's like a quanta of thought, I guess. It measures to like 100, 200, 400 milliseconds, something like that.
Yeah.
And so if you're able to enter into coherence with the Schumann resonances for just a few seconds, you could have perhaps a few thoughts like pop into your brain that maybe were stored in the Earth resonant field. That's not just from us, but from all life. And there's more to it than that as well.
How do we measure this and study this?
The Schumann resonances?
Yeah,
or
like if this idea that these ideas can be stored in this specific resonance and it have the human brain be able to pick it up simultaneously on opposite ends of the Earth.
Yeah, that would be...
Has anyone ever tried that?
Not exactly like that, but there has been a lot of work adjacent to that. There's been work looking at people's like biosignatures, and then what happens to Schumann resonances, and then like a solar storm impact, and seeing how that affects their heart and their brain waves and everything, which is kind of related, but not exactly. But for that, I guess you would need a good enough receiver and a good enough transmitter. So I would think that, and you probably need a big sample size of multiple times. So maybe like some mass meditation event of thousands of people in India, let's say, focusing on one idea.
Right.
And then a receiving group in meditation in South America, let's say, trying to receive that and then doing that over and over and over to see maybe if they can pull in the information. There's probably a more elegant experimental design that you can make, but just off the top of my head, I don't know. It's kind of it connects into these esoteric realms of how do you like measure this stuff?
Exactly.
There's enough data there to point to something that's interesting, but then in terms of like, how can we prove it? Is this in a field that's beyond our ability to prove empirically? Like, is this just too right brain to do that?
Right. Well, I mean, a lot of this type of stuff that you're talking about, you can't really use the scientific method to figure it out, right? Like it doesn't pass scientific method muster, these kinds of ideas.
I think we'll look back in like 500 years and we'll see the scientific method and the scientific revolution as a really cool thing, but just as a stepping stone to more integrated approach.
Yeah. Which is, that's a wild thing too, is like the foundation of the scientific method hasn't really evolved much, right? Like everything is just kind of like floats on top of that. And we haven't really like adapted that foundation very much. We've stuck to that rigid foundation, and I feel like it has to evolve.
We know it's not 100% correct because when the scientific method and the consensus right now is that consciousness is just an epiphenomenon that just manifests somehow in the human brain and basically nowhere else, then it's like, okay, guys, like this is nonsense. So there's a whole bunch, like the Big Bang is another example of that.
Yes.
It's just, guys, there's more to this. Like consciousness isn't, if we're the only conscious beings in the universe and then everything else is not conscious and just completely materialistic and doesn't matter, then what does that say about us?
Right.
Like everything except us is not conscious, but it makes us puny in comparison because we're basically a speck of nothing in the vastness of the universe. So there's just some problems with the scientific foundation. I think we'll look at it in the future as one tool of many to use. And I think the science of the future is going to be more a science of consciousness exploration. But how is that going to be done? And, what methods actually turn out to be like verifiable across time?
Yeah.
I'm not sure, like remote viewing is that.
Yeah, definitely falls into that category.
There's remote viewing. It's all the 4 million draconians on 3i Atlas. So
remote viewing found that?
Yeah, that's what some people said. Like, I'm seeing 4,000.
Oh my God.
4 million draconians. So there's a lot of just nonsense
there's
out there.
Just so much nonsense. But there's so many charlatans out there, man.
Yeah. It's a low consciousness mindset. Like, the Yuga cycle, are you aware of like the Yugas?
Not super familiar.
I'm sure you're aware of like the 24,000 roughly
Yes.
year precessional cycle
Of the equinox, yeah.
Yeah, and then the Greeks have what they call the Great Year. Which
Oh, yeah, I'm
falls in
familiar
line
with
that.
this, yes.
The Yuga cycle is the same. It's just the Indian version that we go through cycles of consciousness. And right now, supposedly, we're basically at the bottom. And that,
Really?
well, there's two different main ideas. The main one of them is that we were at the absolute bottom of the consciousness cycle with the fall of the Roman Empire around 500 AD, which makes a lot of sense. Our history of 500 AD is almost non-existent for at least Europe and
That's when we went into the
Rome.
Dark Ages, right?
Exactly.
Yes.
500, 600 AD, almost no record of anything. So it was definitely a dark period in time for Europe. You know, other
Yep.
places it was different.
That was right when they destroyed the Temple of Eleusis and got rid of all magic, right? That's when the church got its hold, right? That's when basically Christianity became like the dominant thing. They destroyed all paganism. All the other religions kind of went away. That's when the church took hold and basically like everything, like science and everything, went stagnant.
Effectively, I mean, the Temple of Isis in Egypt was the last cult temple to be active in Egypt, and that was going through even the Roman Empire. That also collapsed around 500 AD. So that's one time point for the bottom of the Yuga cycle. It's called the Kali Yuga, where the lowest consciousness is just materialistic. Everyone's liars and cheaters and more. And then we'll ascend up into different yugas. There's the Dwapara Yuga, the Treta Yuga, and these are more enlightened states. And the other idea is that we're at the bottom of the Kali Yuga right now. In 2025, that was the bottom of the Kali Yuga. So there's some
Wouldn't be surprised, man.
conflicting ideas, but it does seem we're more on the ascent, like the ascent up out of it, because we're coming to more like energy-based technology and understanding of frequency and information and such. And that seems to have existed also in the past too. With, like, for example, we've been talking about the pyramids. Some of these ancient sites, this kind of more macro, greater understanding of the flow of energy around the planet. I think there's enough evidence there to say that probably was the case, at least with certain maybe more educated groups like the Druids, perhaps, right? Like this. So we've seen, and there's like the Babylon Battery, and we had evidence that they were aware of some of these things in the past, and then we really dipped out of it, and now we seem to be coming back into it. But I guess according to that, in 12,000 years, we're all going to be enlightened masters walking on the planet. Sounds pretty great. But
yeah, if we can survive the machine rapture that's coming.
yeah. That'll be our test to see if we actually learned something, I guess, from Kali Yuga.
Yeah, it's scary. But listen, man, we just did like 3.5 hours. Thank you so much for doing this. I learned a lot. Tell people where they can find you on YouTube, social media, and all that stuff.
Sure. Yeah. Thanks. My YouTube channel is at Stefan Burns. So STEFANBURNS. And then my X account, which I post updates there in between videos, would be same Stefan Burns, but then also Geo. So STEFANBURNSGEO. And I also have a website that's earthevolution.com. I sell holistic wellness products and some merch there. It's just some basic stuff. But the YouTube channel, I'm posting video almost every day. I'm starting to do more podcast interviews. So it's a good spot. You'll learn a lot if you watch videos across time. You'll learn about all this stuff.
Holy shit, dude. You got a huge audience on your YouTube channel. That's amazing.
It's been great. People are loving it.
It's impressive stuff, man.
I think it's mainly because I'm independent and just chasing this out and trying to understand it. And, I have my own thoughts and beliefs, but I'm not too attached to anything. So I think that's kind of the key going forward. And
definitely
just wanting to deliver good information to people and keep a roof over my head.
Yeah.
So that's really, those are and better understand the earth, the sun, all that. Those are my goals.
Well, good stuff, man. I really enjoyed this and I learned a lot. I'll link all your stuff below, people to find it. That's all, folks.